All right, so it looks like the stream is live. Hopefully there's no weird audio issues. If anybody's tuned in there online, feel free to use the chat and let us know that there are any problems. In the meantime, I'll go ahead and introduce myself. I'm Brandon Litherland here from NASA Langley Research Center, co-host of the 2025 OpenVSP Workshop here with Rob McDonald, the developer and lead of OpenVSP. So we're just about 4 minutes away or so from kicking off the content this year. Anybody tuned in online on the YouTube stream should be able to see closed captions for any of those that are hearing impaired or just want to turn the volume down and read along. But we are running with about a 15-second latency or so. So if anything comes up, you have to wait at least that long for us to be able to see it and respond to you. But otherwise, everything should go pretty smoothly. We've got 3 full days of content for you, starting with today. And Rob, you're welcome to chime in here if you've got any tidbits or a little preview of the agenda for the folks online. But otherwise, we'll be set up to start here in just a few minutes.
I think that covers it, Brandon. Thanks a lot. Looking forward to getting started.
All right. All right. I think we're close enough here to the top of the hour, and we just hit 11. So, Rob, you're welcome to go ahead and kick us off.
Well, thank you very much, Brandon. Welcome everyone who's out there listening and on the recording to the 2025 OpenVSP Workshop. And I'll just go ahead and get started. So I wanted to first talk about some of the things that influence my perspective on creative productivity and some of the technology things that we maybe have something to do with. And there will be a point, I promise. There was some interesting research done back in the late 70s and early 80s by IBM predominantly, looking at interactive response time and what that meant for creativity and productivity. And they did some studies, and this was mostly using dumb terminals interfacing with mainframe computers. And so what they're looking for is the system response time down here on the x-axis is what the time was between typing in an entry to the dumb terminal and when you got a response back from the mainframe. And of course, what they found was that there was this highly nonlinear effect of getting very, very low latency, very short system response time that would result in in a huge increase in productivity and output, how many transactions someone could handle. And there was lots of other research that was done similarly, looking at other measures of systems response time in different cases and looking at what was the productivity coming out. And the short version of this is that in a creative process, your ability to be creative and stay focused on something and to iterate on ideas and to produce output is very much related to how quickly the system responds. And so that can be very short latency, like these, where they're measuring it in seconds or milliseconds, but it can also be much longer. So for example, if you're doing an analysis and that analysis takes a week to run, then you get very little interaction with it, very little creativity, because every time you spawn off a job, you now go do something else for a week while you wait for a result. And then when that comes back, you have to iterate. And that kills that iteration process. Whereas if you can do an analysis that comes back in seconds or minutes, the shorter time, the better, then it is much, much more conducive to a creative process, an iterative process of design and how we work. So that background really motivates a lot of why OpenVSP is trying to be so fast and do so many of its analyses so quickly. So let's talk about what geometry does in the role of aircraft design. Really, geometry is the start of all kinds of, analysis and design. It is the first step in all of these things: aerodynamics, structures, acoustics, mass properties, RCS, all these things. And we think about back when we were in engineering school, right? When you took statics, one of the most basic engineering classes, at least when I learned statics, step one was always draw a free body diagram, right? When you start engineering analysis, you start with the geometry. And it really, that's pretty universal across most analyses. What's interesting though is that, and that's true across the whatever the analysis is, whatever the fidelity is, and shape is that common denominator. However, in practice, there really is not much commonality between these because of the disparate needs of the analysis of these different things, right? Aerodynamics cares about the OML of the aircraft, whereas packaging and layout cares about all the things on the inside of the aircraft. And they couldn't be any more different in terms of their geometry needs. So the true geometry, what does that mean? What is the true shape of the airplane? And as it turns out, if you go out and walk around in an aircraft, right, the actual physical manifestation of it, that true shape really doesn't correspond one-to-one with any of the particular geometry analysis representations that have gone into that, right? The CAD model is typically built with a single analysis intent. If you're building a CAD model for manufacturing, then you build the model one way. If you're building it to check the integration and maintenance and reachability, can the mechanic get their arm up in that nook and cranny? You build a model a different way. If you're going to do a structural model, then you build the model that way. And often the structural elements don't actually correspond to the CAD model. And what I mean there is you may use beam elements to represent something like a hat section without actually modeling the detailed geometry of that hat section. And of course, aerodynamics, you care about the OML, and then the propulsion is maybe done as a boundary condition. And so, that there isn't necessarily, the analysis doesn't always have to match the geometry in a primitive way. We usually glance over this because we understand what's going on. But in terms of representation, there's actually significant differences here. There's also a modeling gap in the way that we approach geometry and analysis. Historically, every analysis tool had its own geometry engine built in. And so every analysis tool had its own integrated geometry stuff. And it used its own inputs and it performed its own analysis in its own way. And then the sort of what you might consider the more modern approach is using CAD. And so then CAD would then feed a very general purpose measure, whether that was for CFD or FEA or other tools. And so we go from CAD to some sort of an elaborate pre-processing tool to then prepare the input to our code. And, the CAD approach is nice because you might end up with one representation that feeds multiple analyses. But again, you don't really, because you have to model it differently in order to achieve that. Whereas the first approach means that if you have 5 analyses, you end up with 5 different geometry representations, and not just mathematically and conceptually what they represent is different, but the variables, the inputs, and the parameters that represent them are usually different. When you put this together in an actual productive engineering workspace, you usually end up with a single flow from a representation through to a single analysis tool. And this is just human nature, right? We don't have the resources to go and invest in many, many analysis tools and many, many workflows. And so when a company invests in, say, automation and validation and experience in training their team, right? When you invest in one tool, which is the full stack from geometry processing all the way through to a result, when you invest in that, that becomes the tool you use for everything. You use that tool for all levels of analysis, whether that is the best choice or not. And so we end up with a de facto very little choice in analysis fidelity. And if we think about different fidelity levels and different analysis disciplines as a matrix, that we would ideally, in my opinion, like to have as a densely populated matrix that we can choose our analysis and our fidelity based on the problem at any time. In reality, we end up with a very, very sparse matrix where we're lucky to have one analysis for each discipline at all, much less multiple levels of fidelity. So these representations of geometry, this is kind of what I'm talking about. We might represent a wing with an airfoil stack up on the left, or a wireframe drawing, or a wireframe representation, or a smooth, analytical Bezier surface representation up on the right. We might have an unstructured surface mesh, or maybe a panel code mesh, or maybe a thin potato chip vortex lattice simulation. Down on the left, we might have a finite element mesh representing, the wings and the ribs and spars and the wing's surface. We might have an equivalent flat plate representation, or down on the bottom right, we might have an equivalent beam for that wing. And so right here's this, very quickly 9 different representations of a geometry that would feed different analysis tools. And, in a traditional CAD workflow or in a traditional geometry workflow, these aren't easily available. And when I made this figure first, many, many years ago, I had to cartoon all of these up. I had to sort of manually create them. And it was a bit of, movie magic to make this figure exist. Whereas today, OpenVSP basically supports all of these directly, which is, I think, really exciting. So really, in a VSP setting, all of these representations can be generated from VSP. And so the shape, the fundamental, what is the geometry, as far as what OpenVSP stores and keeps in memory and saves to disk, right? We're not saving any of these representations. What we save is the parameters, right? The parameters that you're adjusting in VSP, those parameters are the geometry. And all of these different representations are created as needed. Sometimes that's on the fly, but sometimes it's through an explicit action. Now, the representation, it relates to the discipline, and as I've said, and it also relates to the fidelity. So, a vortex lattice simulation needs one representation, a panel code another, and CFD another representation. So the representation may relate to fidelity, but the important thing here is that people often mistake that for the stage of design. Some people think that you use low fidelity tools in conceptual design and higher fidelity tools in preliminary and then highest fidelity in detail. And that's not actually how the mapping goes. There are times when it is appropriate to use low fidelity tools very late in the life cycle of a project, and times when it's appropriate to use high fidelity tools very early in the life cycle of a project, right? So it's not this monotonic low to high as a program progresses. So let's talk a bit more about fidelity in the design process. This is my soapbox. I get this moment. So first, I'll share a figure from my late friend Lee Nicolai's textbook. This is from the 2010 edition of his book, but if you look in the 1976 edition, it's the exact same figure. It just wasn't in color. And so Lee's talking about, the conceptual design process and the aircraft design process from conceptual to preliminary to detail. And when you look at this, we're looking at, well, what are the things that are being considered? The overall shape, sort of the details here, and then, really the details, the ply layups and the structural details. We look at the results and what's the output. And the point here is all of this is about what decisions are being made in the design process, not about how those decisions are being made. Nothing here talks about how they're made. And so sometimes that to make those decisions, we need sophisticated analyses early on, but sometimes we don't. And so, in this process, there are times when you need a sophisticated transonic CFD code in early conceptual design. And there are times when you're going to do paper and pencil analysis of the loads on a bracket in a structure very late in detail design. And, that's entirely appropriate, choosing the fidelity as you go. I have a little bit different perspective up here on conceptual design. And what I really like to teach, and when I did that, is that the real outcome of a conceptual design process, of a conceptual design program, the real outcome is not the airplane design. The output of that is actually a go, no-go decision by your leadership. And a conceptual design process is all about leading up to that go, no-go decision. Does this program continue? And there have certainly been cases where successful conceptual design processes have gotten to that point, they've made a go decision, and then they throw out the design and they start over. And that's okay. And so when you think about conceptual design decisions, and when you think about the conceptual design process, you need to think about them with respect to that go, no-go decision. Does whatever rabbit hole you're going down and whatever, fidelity and whatever decision you're trying to make or add to the simulation, does that thing influence whether it's going to be a go or a no-go decision? And if it doesn't make a difference, then you're not spending your time on the right thing. You need to be focused on what influences the go, no-go decision during conceptual design. So OpenVSP uses parametric design, and I talked about how the shape and what the representation that VSP has really is those parameters. And what I'd say is that's true throughout all phases of design. It's just what those parameters are evolves. So early in the conceptual design process, we have these very high level parameters like aspect ratio, area, sweep angle, taper, thickness to chord. And then as we move to preliminary, we're talking about more nuanced, twist distributions, thickness to chord distributions, a complex wing plan form, detailed high lift geometry, control surfaces, all of this kind of a thing. And so we have more parameters and they've evolved. And then we go all the way to detail design, where to some extent the generalization of parameterization may break down, but the parameters at that point are the angles and the dimension drawings and what are the dimensions in that drawing. And so again, as we move through design, what phase of design is based on what decisions are being made, not how they're being made. So let's talk a little bit more about the design process. Another soapbox for me. A rational aircraft design process. This is the way it should work. We start with a mission, and the mission is there to answer the question, what is the aircraft going to do? And we move from there to the ConOps. And how is the aircraft going to do that? So what is the aircraft going to do? We're going to move people around inside a city. The ConOps, how are we going to do that? We're going to take off and land vertically, and we're going to move very quickly, and we're going to recharge very quickly. And you take your mission and your ConOps, and then you can start to set the requirements. You use those and you figure out, okay, I need to carry this many people. I need to go this fast. I need to fly this often. I need to be able to take off and land out of this size of a heliport or a landing field. And we're quantifying the requirements for that ConOps and for that mission. Only at that point should we then move to starting to define the concepts. And here, when we're looking at these concepts, we're looking at the system architecture. Is this going to be a jet wing? Is it going to be a tilt wing? Is it going to be a fixed wing aircraft? Is it going to be distributed electric? Is it going to be, just whatever that conceptual architecture is? You can think of these as discrete big block things. And then when we have a concept, then we can move to these more design decisions. And where the concept decisions are laying out the system architecture, the design decisions are actually then tuning those continuous parameters. Oh, well, what's the diameter of the prop? What's the wingspan? What is the thickness? So we go through a discrete variable phase, and then we move into a continuous variable phase. And this is the way advanced design should work. And note down here at the bottom, these last two steps, 4 and 5, is really where we would like to look at many concepts. You're not really doing conceptual design if you don't compare at least two concepts and decide which one is better. So if we want to look at many concepts and concepts, we are going to be doing iteration, and we are going to be doing trade studies. We're going to be doing trade studies to set the continuous variables, and we're going to be doing iteration over concepts. And so we really need to enable as much speed and as much iteration in those two steps. Now, as we look at the larger picture of a life cycle, we move out of that conceptual design, we go to preliminary detail design, test and cert, manufacturing, tooling, operations throughout the whole life cycle of the aircraft and disposal. You'll notice as we move through this process, we have less and less design freedom, right? We've committed more and more cost. Even if we haven't spent that money, when we decide that we're going to do a particular engine architecture, or when we decide we're going to use all composites, or when we decide, how we're going to lay up those composites, we are committing costs. We haven't necessarily spent the money yet, but we've decided that if the program continues, we're going to have to spend that money. And as we commit those costs and as we decrease our design freedom, the cost to change a design increases exponentially. And that's obvious that if you need to, make a major change to a design after you've started manufacturing, that's incredibly expensive. But it's true through all of these steps that the further you go in this process, it's more expensive to make a change. And that means that you just want to make all those changes up front. You want to make those decisions when it's cheap, before you've committed the cost, before making that decision gets expensive. And so you want to do this in a rational way and proceed. Now, unfortunately, the reason I talk about the way it should work is because, unfortunately, very often these days, it seems that it doesn't work that way. And I will say that there's a lot of quote unquote innovators out there in the aircraft design space where the process doesn't follow what I've laid out. And instead, it typically starts with somebody who's had a decision about what the concept ought to be. And they make that concept decision up front. They've decided this is the concept. It's probably an arbitrary decision because they didn't actually do any trades or any comparison, and they make that way too early. And now that they have their concept, they hire an engineering team and they throw that over the wall and they say, make it work. Try and figure out how to make this happen. Take this concept, make an airplane. And what we find is as they proceed in that, then they go out looking for a mission. Okay, well, we've got a concept. We're going to have an airplane. What on earth is this thing going to do? So we go searching for a purpose. What's the point of having this aircraft? And they move from that to then, well, now we've got an aircraft already defined, and now we found a mission. So now we force the ConOps to fit our aircraft. We're just trying to shoehorn it into a particular ConOps. And this process is very awkward. And the thing that's missing from this is the requirements, right? Nobody ever states the requirements. And so the engineers in step 2 are fundamentally working to an ill-posed problem because they don't have requirements to design to. And they're just going to treat the requirements as a fallout. It can do whatever it can do, and whether that meets the mission in the ConOps or not, oh well. And what's really missing here is iteration, and you end up with teams that are completely married to a concept. And that's, fundamentally a bad way to go. And I've seen way too much of this. Now I'll juxtapose this and I'll put in with this that, I think fidelity is used poorly today in engineering. I think it's all too easy to push for quote unquote higher fidelity. There's this constant push. People seldom get fired for using too high fidelity of analysis. And Moore's law justifies and enables this continuous increase in fidelity. And there I'll just say that I'm saying the number of floating point operations per answer. What is the computational cost? Even though that's often increasing fidelity per answer, but at constant calendar time. I feel that if you went back to the early days of CFD and you tracked the wall time of the top of the line, state of the art CFD analysis, that it would stay about the same. It's about 1 week. And from the birth of CFD to today, that's remained essentially constant. The top of the line CFD analysis remains 1 week. And I would argue that that is not because that is the analysis fidelity that is required or that is needed, but it's just because that's what they can accomplish and what they have the patience for. So the pursuit of fidelity is actually separate from the actual needs of programs and analyses. So I'll go a little further. We often see, and I'm talking specifically in eVTOL, just because that's an area that I have a lot of familiarity with. You'll see these marquee CFD calculations where you have an animated high color rotating blades, elaborate color video that's the result of a weeks-long supercomputer analysis. And what I'd say is that these stunts, these analyses are essentially meaningless in the design process. And the reason for that is that they're almost always done at a single operating condition and at a single, angle of attack, forward speed, climb speed. These are over-controlled vehicles with many different flippers and RPM and rotor pitch on them, so many, many degrees of freedom to control them. And yet the simulation is done completely untrimmed. It's just a fixed RPM, fixed angles on everything that we can do it. Whereas in reality of this kind of vehicle, it's the off-nominal analyses that dominate the design, and you need tons and tons of these. And so these one-off stunt calculations are actually meaningless and perhaps dangerous. The highest fidelity analysis tools and become unavoidably black box, right? Even if you are the developer of a Lattice-Boltzmann CFD tool, you lose intuition for what changes to the inputs are going to have in those detailed outputs. Even the most expert person on these ends up being forced to use these tools as a black box because we have this opaque mapping of inputs to outputs. They produce gigabytes of output on every case, and then we boil it down to just a few coefficients. And really the outcome for this, in my opinion, is that when an engineer chooses to use a high fidelity tool, they may or may not have understanding of the problem. And that choice of using a high fidelity tool does not demonstrate that they know that they understand the problem. They very well may just be, I don't know, so I'm going to throw the high fidelity at it. On the opposite side, if we go back to this rational design process where we need to look at multiple concepts and we need to iterate and do trades in order to make those decisions when they cost the least, fast, inexpensive tools are essential to conceptual design. We need to look at more concepts, more iteration, more trades, more insight. And all of this enables the creative process, getting that response time down and being able to do these things. And so the goal should always be, in my opinion, to use the lowest fidelity tool possible for all decisions. And I'm not saying that recklessly. You have to know that the tool is sufficient to make the decision. You have to understand the problem well enough in order to know that that tool can support the decision you want to make. And so consequently, if you do this and you're successful, then appropriate use of low fidelity tools does demonstrate that you understand the problem and that you understand the decisions you're making. So let's talk a little bit about OpenVSP. That's my rant to start the morning. Here we are, we're in 2025. I think we've had 13 or 14 different OpenVSP workshops, which has been amazing because when we did the first one, we didn't know it was going to become an annual event. It was just the OpenVSP workshop. So, I ask out there every year, I ask how many of these have someone been to? And ask yourself also, what version of the software are you using? And so right now, the current version is 3.43.1. And if you're using 3.25 or something, come on, guys, it's time to update. Since last year, there's been just a litany of features that have been added. I'm not going to read this list. There have also been countless bug fixes. A lot of the workshop this year is about talking about these new features. I'm really excited about a bunch of them, and I hope that you guys are going to enjoy it. It should be a lot of fun. Here's the agenda. This is posted on the wiki page that if you found the link to come to the stream, you know where that is. We're going to take the calendar here is a little bit odd. I have Pacific time on the left, on the west, and Eastern time on the right. It's very US centric, but hopefully that gets most people oriented for what's going on here. And so we have a break for lunchtime on the East Coast and a break for lunchtime on the West Coast as well. And after my talk right here this morning, we're going to turn it over, and Brandon is going to do a great demo of modeling a realistic and interesting aircraft. And that's my last slide. I'll go look at the comments to see if there's any questions that I've missed. And I'm really just thrilled that people have joined us and that we get to do this today.
Thanks a lot, Rob, and great intro. So we've got a couple of people chatting here on the YouTube channel, but for the most part, we've got people tuning in, and I think I should be able to just go ahead and get things set up for our demo. For those of you online, this next session, as you can see in the agenda here, we're going to spend about an hour working through a tilt wing concept. So while we're doing that, we are just going to build it up. It's going to be based on the NASA UAM reference vehicles. So while I have this, let me just pull that up and show you all what that looks like. So here we have our web page for the NASA
You're not
reference.
sharing yet, Brandon.
Well, I'm sharing it on the stream. I'm not sharing it to the teams. I'll switch that up so that you can see what I'm doing. Just a sec. Hopefully it doesn't freak out if I'm doing two things at once. But okay. So here we go. We've got some of our 6-passenger UAM reference vehicles, tilt duct, tilt wing, tilt rotor, lots of stuff. The nice thing about each of these is that they come with the documentation, or essentially the white paper that was published sizing each of these aircraft. You've got in-dark models and the OpenVSP models for all of them. So if you want to go in and pull down one of these NASA OpenVSP models, they're released. You can start there, play around with them, and turn them into your own thing. So with that in mind, I saw that there are some new folks joining in and joining the chat. Thank you all very much for tuning in. Welcome. If you haven't been there yet, I wanted to point out to everyone that the OpenVSP Ground School is still up and running, and it's vspu.lark.nasa.gov, and I posted a link there in the chat. That's where you can go and visit this if you want. When you land here, there are lots and lots and lots of tutorials, and anyone that's revisiting that's seen these before is probably getting sick and tired of hearing my voice, but one that I like to point people to is this introduction to the basic modeling process. And so each one of these tutorials, if you click on it, it will show you where you are in the training library. It has a brief introduction and then a short YouTube video walking you through that individual step. So what we're going to do is go through this live by essentially building an aircraft on the fly. Now, as is historic with OpenVSP demos, something may go wrong and it'll crash, so I'll save often. But for the meantime, I'm going to go ahead and minimize this and bring up OpenVSP so we can go ahead and get started. So let me resize some of my screen so that everything looks pretty good here, and then we'll start playing around with this. Bring that out to about here. That looks about right. Okay, so from here, we're going to go ahead and build an aircraft. Now, the great thing about OpenVSP is this doesn't take very long at all. So all we have to do is, like Rob said, define what's the mission, what's the point of it. Well, in this case, our point is to carry about 6 passengers. So the first thing that we need to do is add some passengers. So there is a handy little human geometry here. And if I fit this to my screen, it's a wireframe mesh. There are presentations at previous OpenVSP workshops that go into exactly how this thing is built and manipulated, but it's a really handy feature. So for starters, we're going to change it from a standing to a sitting pose. All right. And based on what we have on defaults here, this is just a regular, certain age percentage male body in a mesh format. So what we're going to do is I'm going to make 2 of them side by side by turning on our XZ symmetry about its own reference, and I'm going to separate them a little bit with this slider here. And so I think about 1 foot or so away from center line is good. They might rub elbows a little bit, but that's not really a big deal. Okay, so now that we have that, let's go ahead and make another row. Now in this case, I can just copy, paste, and you can see here that this is now what's called a child of this ancestor. So they're right on top of each other, but if I move them aft, here we go, we've got our second row. So now we have 4 passengers. I'm going to set this to about 2.5, give everybody a little bit of knee room. And now I'm going to attach this to the parent. So in this case, I'm going to turn on component translation here. Okay, now notice that it shifted based on this 1 unit to the right. That wasn't really what we intended. We're going to get rid of this Y separation, but then where did our second person go? That's because our symmetry is about itself. We need to go and make it about, or I'm sorry, it needs to be about itself, not its ancestor. So here we are, we've got our second row of passengers. So all we're going to do is repeat this process, copy them, paste another row. Again, we need to change that ancestor right here. And now we've got our 3 rows and our 6 passengers. Excellent. So while I'm at it, if we come in here, there's a fast way to just change this from a male to a female representative body. We can come into pose. We're going to change some of this elbow angle to try and bring the arms in just a little bit. Okay, so now we have our passengers. So anyone that has used OpenVSP for a while knows that if things are going to go wrong, we need to save, because there is no autosave in OpenVSP. So what we will do here is we are just going to save as Tiltwing Demo 1. Okay. Now we have a backup, and if everything crashes, we can just open it back up and get back to it. Okay. So the next thing that we're going to do is we're going to add a fuselage to carry these people. Okay, so we're going to add that in. By default, this is about 30 feet long or so, clearly the wrong shape for what we need. So under our design tab, we can change the length, we can move things around. What we really need to do is put this around these people. So just for starters, I'm going to move it forward to about here, I think. That might even be a little bit too far. Let's back it up about 6 feet or so. And then in the design tab, let's set this to something like, 25 feet instead of 30 feet. And even then, that might be a little bit big, but we'll see how it goes. So as we're doing this, we need to adjust these cross sections inside. So right now, the tip is a point. We come out to the next cross section, And here, that's essentially this cross section. So we can adjust the width, you can see here from the front, and we can adjust the height, because right now we're set to an elliptical cross section. So an ellipse is a fair place to start. We could change the shape of this, and we probably will later, but for right now, let's stick with that. So instead of having it sit right there, let's nudge it forward a little bit, put it right underneath that front row feet, and we'll set this to something like 6 feet tall, and we're not too bad on the width, but let's make it, say, 5.5. Okay, so instead of having to go through that whole process again, I'm going to copy this and just paste it at the next cross section. All right, so now we have something resembling a cabin. That cross section again is probably a little bit too far aft. We're going to bring it forward. And now we're starting to get something representative of a shape. So in the next cross section, we can move that around all the way back if we want to, and we can start to shape this stuff. So while we're at it, let's go ahead and make this a circle. We're going to change the diameter so that it's a bit more like a tail, maybe something like 1 foot or so. We don't have to be really fancy with it. And then what we're going to do now is we're going to shift this up. We want to have something that's a bit more of a flat shape here on top. Now don't worry about that weird little ghost tail at the back. We're going to fix that too. Let's make this about 1.5. That seems about right. So back here at this closeout point, all we need to do now is set that Z to match, about 1.5. Okay, no big deal there. Why don't we go ahead and nudge this a little bit more? Okay, so now we have something kind of resembling a fuselage to carry these people around. We can refine this a little bit if we want to play with some of the cross sections, maybe dip this nose down some. All right, no problem there. Let's make it a little blunt. Now, in skinning, for anyone that hasn't tested the modeling yet, let me go to a nice side view so you can all see what I'm doing. So in skinning, you're effectively changing the strengths and angles of how the curve flows through each one of these cross sections. So I'll give a brief demonstration here. Top side of this 0 section, you can see is set to 45 degrees and it's moving up. If I bring that down, it makes it more acute. If I make it bigger, it increases the angle. Now we have top-bottom symmetry turned on at the moment, and that's fine. We also have left-right symmetry turned on. If we turn that off, we can adjust the bottom independent of the top section of that curve. So for now, I want to set both of these to 90 because I want kind of a blunt nose on this thing. But I think the strength is a little bit too much, so we're going to dial that back. Maybe something like 0.3 is fine down there. And 0.3, nope, not 3, 0.3 is about right there. Okay, so same thing here. We're going to do 90. Now, even though the front of this still looks faceted and kind of sharp, you can see the curve is smooth. So if I come in to our section, come back here to 1, I can increase the number of U panels between this section and the previous one, and we can make that smoother. So I can give this any number I like. That seems fine, but you can see we get a reasonable, smooth front end to this fuselage. If we want to make it a little smoother on the way around, we're talking about num W. So we can increase the resolution as we go around. There we go. So now we've got a fuselage to carry these people around. If we wanted, we could go in and change some of the shapes of the cross sections. We can refine this a little bit. And maybe we'll do that a little bit later. But for now, let's move on to some other components. We know that if we happen to move this, we want the humans to move with it. And with recent additions to OpenVSP, we have the ability to change around the hierarchy inside this tree that we have. So really, we want the fuselage to kind of be our beginning. And now we want the humans and everything underneath to be children of that. So the first thing I'm going to do is save this model in case things go wrong. And then I'm going to nudge them inside. So you notice I push this button it made that component a child of the fuselage, and now they're all matched. Now, if I want these individuals to move along with the fuselage, I need to attach them. So in this case, we're going to attach it to the component, but you notice that it shifted everybody forward. That wasn't really what we wanted it to do. So if we come back to none, now we can click absolute coordinates, then attach in both translate and rotate. Now we can come back and turn relative back on. So that keeps them locked in their current position. You can change the attachment, and then they stay in position when you reattach them to everything else. So if I were to come in here and now move around this, oops, sorry, wrong one. So if I come into the fuselage and pick the right component, I can play around with this, and now the humans move along with it. So we'll just set that back to -6. The other thing that we can do, say we want to roll things around. Now, you notice that the front row is rotating along with the body, but only the others are rotating as well. That's because they are not set to rotate with the component. We need to fix that. So here, again, we're going to absolute, turn on component rotation, come back to relative, absolute, turn on component rotation, back to relative. Now, if we rotate around, you can see that everybody moves along with this body. So if you're trying to change the orientation of your vehicle, you're trying to move things around, do collision detection, stuff like that, it's important that the stuff inside the component moves along with it. So now that we have that set up, now we can move on to the wing. So here in our geometry browser, we're going to pick the wing component. Again, we'll make it a child of the fuselage. We can add it. So here we go. We've got the fuselage geometry. The wing is down here, and it's just dropped it in space. Okay, so for something about this size, we need to adjust the plan form. We can do that either under the Plan tab, where we're changing the overall wing shape, or we can come in and adjust it by section. So if we jump to a top view here, let's change the span to something like 40. Well, maybe 45. Let's make it a little bigger. And then we can come in and start to play around with some of these other features. So let's make, now we can leave the root chord at 4. Let's change the tip chord to something like 2.3. 30 degrees is an awful lot of sweep for this. Let's change that to something like 5. That seems a bit more reasonable. We can give it some extra sections if we want to, but for the purposes of this demo, that's not really necessary. And now that I look at it, maybe that was a little big. We'll do 3.5 down at the root. Okay, so we're starting to get something that's a reasonable shape. Now, if you remember from Rob's discussion, there's a reason to size all these a certain way. In this example, we're just putting stuff together and essentially making a cartoon aircraft. I'm basing the numbers of these dimensions on the white paper that I referenced earlier. So the sizing, the decisions that went into every single one of these was already made. But before we make a real educated guess into how to put these things together, how big that wing actually needs to be, the analysis should be performed so that you know you have enough wing area to actually pull this off. So anybody that's curious about why I'm picking the numbers that I am, go look at the white paper, the tech memo on the tilt wing aircraft, and you'll see where I got these numbers. So now we have our wing. Again, it's not really attached to anything, but we can turn it on, say component in both translation and rotation. We're going to move it back to about there, call it 6 feet aft, and we're going to move it up to the top of the aircraft. So this will be a little easier to see if we do a left-hand view. Nudge this up about there. Not too bad. So we haven't changed the airfoil, we haven't changed the thickness, we've done none of that, but that's okay. Now remember, for this, we're making a tilt wing. So what we would like to do, we can set a hinge and make that control the rotation of this whole thing, or we can change the rotation itself. Now, if we just come back and start playing around with the Y rotation, you notice it rotates at the leading edge. If I zoom in a bit, it'll make it a bit more clear. So it's rotating essentially at the 0x relative to the airfoil. We can change that position anywhere from 0 to 1 along this section. So now if I start to rotate, you can see it rotates about the trailing edge. So without yet going into a bunch of steps to try and make a hinge and everything else, we can just set this to something like 0.7. Let's assume that we have a spar back there. And now the wing can rotate. And if you notice, as I'm coming up against this button here, it's changing from an inside arrow to an outside arrow. Anyone that hasn't seen this behavior before, if you click on this, it increases the range of the slider. So now we can go all the way up to 90 degrees or beyond and rotate down. So we can go as far or as short as we want. If you find that that range is too big, simply click on the collapse button and that will shorten the range. Now we have a smaller segment that we walk through. All right, so now we've got our wing, we've got a fuselage, we've got some people in it. Let's go ahead and save again to make sure that we don't crash anything out. And we are going to add some propellers. So let's do that next. In order for this to take off vertically, of course, it has to have rotors. So we're going to grab a prop component and we're going to add that under the wing. Okay, so our default propeller is 30 units in its diameter. That's far too big for what we're doing here. So I think what we'll do is set this to something closer to 7.3, something like that. And we can make this a 5-bladed rotor. And if we have time, which it looks like we probably will, we'll come back and maybe play around with some of the blade curves and give you some demonstrations of that. Now, again, this isn't attached to anything. So we need to put this on the wing. So right now, we've got people, we've got a fuselage, we have a wing. Things are starting to get a little bit more complicated. Just as a general demonstration, under the General tab, if we want to change the color of the fuselage wireframe, we can choose any of these colors here. We can also shade it under any of the default materials, or you can make a custom material. So for this, let's go ahead and call the material a nice medium darkness glass, and we can shade this fuselage. Now we can see inside it. The people, if we want to select the human geom or use this button to collapse the whole list down, we can hide them or show them. We can also change the color, of course, but for now, let's just hide them away. We know they're there, but we don't need to see them at the moment. So for our propeller, instead of attaching in component, what we really want to do is attach it to a certain position on the wing. Now we can do this a number of different ways. There are other presentations where we talk about attachment and rotation with parent and child in the ground school. For here, we're probably just going to set this to something like eta. So now, down here, we can set this as a function of essentially the span or the semi-span. Now, if we would have had, say, a multi-section wing, the U parameter gets broken up where all the way down here at the root, and by the U coordinate, I just mean the surface that represents the outside of this wing. So down here at this line along the chord at the root is U0. And then because this is essentially a one-section wing, this is 1 or 1/3, 2/3 is all the way out here at the tip, and then 3/3 is the end. So if you happen to have your coordinates based in something like UW, if you split the wing, all of a sudden that U coordinate changes. The eta parameter lets you place it along the wing and it stays fixed. So notice how all these are updating. So what we want to do is we're going to attach it out to essentially the wingtip, okay? And we want this to be all the way forward. Now it's attached at the leading edge of the wingtip, but notice it's still not quite rotated where we want it to be. Let's put the wing back to 0, just so that we have everything in the position that we want it to be. We're going to take the propeller, let's move it forward, say 1.5, and let's move it down just a little bit, so 0.5. That should give us just enough room for a nacelle out there. All right, so we jump to a front view. We can kind of see where this rotor is going to live. In this case, now we want to attach it to the component rotation. We want it to move with it. So I've activated the rotation. Notice that because it wasn't rotated at all, it didn't move, it didn't do anything. But what should happen now is if I change our rotation, now our propeller moves. So I can rotate this around, and the propeller rotates along with the wing just like it should. All right, so that was a successful addition of a prop. If we want one on the other side, you can either add a completely unique prop component over to the other side and repeat the process that we just did, or you can just turn on symmetry. Again, it's symmetric about itself at the moment. We want it to be symmetric about the wing or its ancestor. So now it popped it over to the other side. Symmetry applies to both the geometry itself and the direction of rotation. So if I zoom in, and you can see here at the wingtip, this propeller is made to turn essentially outboard down. So it's turning this way. We go and have a look at the other side. The blades are all reversed, and it is turning opposite. It is turning outboard down on the left side. If you have propellers where you want them both rotating the same direction, symmetry will not work for you. You have to create a new propeller geometry out on the other side and turn it. So now that we have that placed, let's go ahead and save before this decides to crash on me. We're going to copy, and we're going to paste. Okay, so same thing. All we're going to do now is change this eta parameter. Now, as we move this in, we're just nudging it a little bit further inboard. Let's put this at, say, eta 0.65. All right. And now we're going to copy again and paste a third. So instead of 0.65, let's make this, no, that's not quite right. Let's do 0.3 maybe. Okay. So those seem spaced fairly evenly, and I don't think we're going to hit the fuselage, but a nice way to check, if we come to the design tab in the prop mode, we can go from blades to disc, and then let's have a look at it from the front. Okay, we've got plenty of clearance, no problem. There are other features in OpenVSP that will let you check these distances and make sure that you're not hitting anything, but for just this quick demonstration that we have, this should be fine. So we have our model, and for the sake of having things speed up just a little bit, I'm going to change all of these to disk. So now we can see where everything is. And note that because I have them attached to the leading edge of this wing, jump to a top view and zoom in, there is already a 5-degree stagger assigned to these. So if I come into the wing, and since we're on the subject of attachment, the reason that I attached it where I did, and you can think about this as a way to easily manipulate a model. Say you set everything up the way you thought it was supposed to be, but now you want to do trade studies on it. Rather than having to go in and individually manipulate each one of these variables for every single component, you have intelligently set these up with the design intent already there. So let's say, instead, I want to come to this section, and instead of 5 degrees of sweep, I want to increase that to something closer to 10. The propellers, everything that is attached to that specific surface is moving along with it. It moves along with it. That's very important, because if you come in and you want to change one thing, everything else is going to automatically update. Similarly, if we wanted to give this some dihedral, the rotors move. So we could give this some anhedral, we can do whatever we want. So just for fun, we'll give it a little bit of anhedral. That's not in the actual model, but we'll do it just for the heck of it. Okay, so now we've got our wing, our prop rotors, our people. We're working our way towards a reasonable aircraft here. So what we'll do next is we're going to add a vertical tail down at the back. In this case, we're going to start with a wing component, add that in, but because we don't need a reflective copy across the center line, under the Transform tab, we're going to turn off the XZ symmetry. And we're going to rotate this about its x-axis by 90 degrees. So now we have a wing that's turned 90 degrees, and we've got a vertical tail. So again, I could just move this thing in space, set it back where I want it to be, and leave it there. But if I start to go play around with, say, the fuselage length or how everything is shaped, that tail's just going to sit there and it's going to be in the wrong spot. So this is how we address that. In this case, let's go ahead and change the name of this wing geom to vertical. So you'll notice that all I had to do was type a new name here and it updated the component. You can also do this under the name button here for any component. So again, this is wing, these are propellers, humans, or fuselage. But we changed the name of our vertical. In its tab, we're going to go ahead and move it about back where we want it to be. Say, here-ish. We're going to come up a little bit, put it about in the middle of the fuselage tail there. Now we're going to change our span to something a bit more reasonable. Call it, say, 4.5 feet. Why not? Okay, so it's still pretty big down here at the root. We don't necessarily need that much. Let's set that something like 3 seems reasonable. Okay, so let's shift this around a little bit more. Call it a square 15 feet. All right. So now, again, we can turn absolute on. It's a child of the fuselage geometry. Instead of attaching it just in component, we can attach it in UW or RST element. These are different kinds of coordinates that are inside the body itself. Because I really want it in reference to this trailing edge point on the fuselage, I'm going to use UW for translation and component for rotation. Now my attachment point here, I want it to be all the way at the back. So I'm going to set this at 1. Notice here, this little dashed coordinate system tells you where the parent or the origin of this component is. So if I walk this back, you can see it's walking along that line and just going along the fuselage. So while we're at it, let me jump to a top view and we'll do just a quick overview of what UW space looks like here. So U, we're going the length of this body. W, we're essentially going around the body. So it starts on the right-hand side, goes all the way around, 0.5 is left, it goes around the bottom, top, and over to the other side. In our case, because we're attaching all the way at the end, it doesn't really matter. But now our attachment point is back here. Great. So now we can come back and turn relative back on. Everything should be attached. And again, if I come up to the fuselage geometry and start to play with it, everything should rotate and move, and it does. Set that back to 0. Good. So again, if I wanted to come in and play around with this geometry, let's go to the fuselage and say, instead of a 25-foot length, now I wanted to make it a little bit longer because I was wrong. Again, the tail is moving. Now you notice that the wing isn't, because the wing is only attached to the component. If we want it to move relative to the body and stay attached in that position, we need to do something a little bit different. So here we're going to set that to 25. Let's come back to the wing and think, what can we do to force it to stay attached to that point? So here it is. Instead of component, we can do UW, or we can switch to volumetric coordinates. So in this case, let's set it to an RST attachment. And now we're going to switch back to relative. So what should happen now, if I come into the fuselage and now start to play around, oh, I picked the wrong component. That was my mistake. So unfortunately, sometimes I go off on a tangent and you guys get to come along for the ride. So we're just kind of doing our thing. That's weird. I see why it's mad. Okay. In this case, I messed up and didn't attach it where I needed to. There we go. So now I've moved the coordinate here closer to where it needs to be on the fuselage itself. Now if I go back to relative, things should work. There we go. Okay. Moving on. So now we have our props, our people, our wing, fuselage, a tail. Again, we're going to save in case this thing crashes out on me. So we're going to add a horizontal tail. Again, we're going to add a wing component. We're going to make it a child of the vertical tail because we want the tails to stay together. Wow, I am sorry for whatever is going on out in the hallway, everybody. Again, we're going to change the name, horizontal tail, and we're going to attach this again in UW. Let's go ahead and set the W to 0.5, which is the leading edge of this geometry here. And then we can set U all the way out to 1. So that'll bring us out to where we're attached here at the leading edge of the tail. We can probably have a little bit more here at the tip of the vertical. Let's adjust that while we're at it here in the section tab. Make that 2. Sure, why not? So because I want those to be essentially equal, I'm going to make my root 2 and my tip 2. And I'm going to set sweep to something else. Let's say 0. Now, that's a little bit too Hershey bar for my liking. So why don't we change this? Let's first move the secondary sweep location off of 1, because you can't have sweep and secondary sweep to be equal. We're going to set the sweep location back to the trailing edge at 1, and we're going to leave sweep at 0. Now, if we adjust our tip chord down a little bit, notice that it's keeping that trailing edge straight, and it's just moving the chord so that it shrinks it back a little bit. So I think that looks a little bit better. We'll do maybe 1.5 out here. Too big of a span, though. So we're going to do something like, yeah, I guess that's actually okay. Let's do 8. Why not? Okay. So relative to these other components, we've got our tails. Let's take a nice front view. In this case, we know that we're going to want to have some prop rotors here at the back that are going to, one, provide some extra thrust, but we also need some stabilizing lift in the back. So once again, we need to come back and add some prop rotors to this thing. So at the moment, let's take one of our propeller geometries here, copy that, and we're going to paste it onto the horizontal component as a child. And because it inherited the attachment properties of its parent, you'll notice that here in the transform tab, it's already got symmetry, it's attached to its parent, and it's already referenced in eta all the way out to the wingtip. And it's got the same X and Z differences here. Okay, so we're not hitting anything. Everything is kind of where it needs to be. Great. But let's assume that the horizontal tail doesn't tilt the way the main wing does. So if we wanted to rotate these, let's have a look at what happens. If we just rotated the propellers all the way back to 90, well, we hit our tail. That's not what we want to do. So there's a way to go about this. Let's set this back to 0. And now we're going to do a hinge geometry, or a hinge component. Instead of leaving the propeller geometry right there where it is, let's come to the horizontal tail. We're going to pick a hinge, and we're going to add that to it. Okay? So a hinge geometry is a handy little feature that acts as either a slider, a rotating component, an axis. You can do all sorts of stuff with this, but for this, we're going to make it a simple rotating component. So here, we're going to choose to place it relative to the horizontal tail. We can place this either in component, we can put it wherever we like. In this case, let's attach it to the tail. We're going to make it in reference to the wingtip. We're going to bring it all the way forward. And now let's say we want this rotation to occur somewhere forward and slightly above where we are now. So some of the relative displacement, we're going to come back, say 6 inches, and we're going to go up about 6 inches, let's say. Or actually, you know what? That would probably work fine, kind of as it is. Let's leave it there. Now that we have this geometry, we need to pick a direction. So instead of using the transform tab, we're going to use the vectors. And in this case, we want to rotate about the y-axis. That's going to be this green line we have here on the screen. And positive rotation is in the direction of this arrow. Okay. So we could just leave it as is. We can choose a vector, and here, notice that everything has turned. We've got rotation of y equals 1. Good. But if we come into the motion tab, moving this around doesn't do anything. Nothing's attached to it. The nice thing about the way OpenVSP now handles parent-child relationships is we can come into this prop, again, turn it back to absolute coordinates so it doesn't move relative to everything else on the space. And now we can nudge it down in the hierarchy, and we can make it a parent of the hinge geometry. So notice that because the parent changed, the symmetry went away. We just need to fix that by making it, again, about the horizontal tail. Okay? So everything now should be set up. And notice that all of the options that I had set for this propeller component got turned off. Anything that becomes a child of a hinge geometry automatically gets attached to it. It's its sole purpose. You don't have the option. But what should happen now is if we come to the hinge component and we go into motion, we can move these around. And so hinge is a very, very versatile component in OpenVSP. Let's say we want to constrain the range. So we activate these buttons. Let's set our minimum to something like 0. Okay. So we can set that. And then for the maximum, we want to set it to something else. So let's move this up to, say, 90. That's where we want it. Great. So instead of having to type this in twice, I can click the set button. What that does is it takes the current value of rotate and assigns it. So here I can bang around, but look, there's all this range here in rotate that I'm not using. So that's not very useful. Let's click on range. Now the min max of this range is set to the min max that we have here. We can go from 0 to 90 in one sweep. And again, anything that we attach to these is going to rotate just the same. So that was a little demo of a hinge component. Again, we're going to save. So now we have an aircraft that is carrying 6 people. Assume we've got some other components down inside. The wing itself, if we come to transform, we can do our rotation about our 70% chord location. Now notice, it's not like a hinge. I can over-rotate. I can do all sorts of stuff with this that I don't intend to. That's why it'd be much better to have this as a hinge, and everything else can be a child of it. You can change one parameter, and then everything updates the way that you intend to. So, in this case, if we did something like, well, let's set the wing tilt to something like 60, and we want our hinge here to set these at 60. Now we can adjust where these discs go, how they're pointing, how everything moves. And again, because we have everything attached, let's say if we came back to the horizontal and decided that we wanted to change the span, the rotors move with it. Everything moves, attachment still works, everything still does exactly what it's supposed to do. So in this case, let's set this down to something like 10. I like that better. There we go. So a nice 10-foot span, everything lined up. Now, one of the things we might want to watch out for, if we set our rotation of the prop rotors back to 0, all right, set our wing back to 0 in our transform tab. If we're looking at it from the front, the prop rotors in the back, which are, trying to either provide thrust, they're trying to lift, they're doing other things, are going to be influenced by these 2 rotors in the front. So they need to be offset a little bit. So there's a number of ways that you can address this. You can either try not to disrupt the flow with the inboard rotors by spinning them very slowly, putting them into a low torque scenario. You can do all sorts of stuff. You could give yourself a bit more anhedral on this side, and you could even come into the horizontal tail, say, well, if we want them to move up, let's just move them up. No big deal. So there are a number of ways that you can try and address this problem, but note that all you have to do in OpenVSP is come in and change one or two parameters, and it changes everything for you if you set up your model correctly. Now, if I didn't have this set up with all the attachment and everything that went in under the design intent, it'd be a mess. I'd have to move all this stuff manually. It'd be terrible. So a lot of the power of OpenVSP comes from the ability to attach and put design intent within the model itself, so that you can go around and change things up. I see that we're getting about 10 minutes past the hour here. I've got about 20 minutes left. So essentially in about 40 minutes, we could cut some of that time off, accounting for some of my little screw-ups that I had. We've put together a reasonable representation of a tilt-wing aircraft carrying 6 people based on the NASA publication. So let's take some time and try and refine this a little bit. Let's save it, again, just in case something goes wrong. And let me, while I've got a nice little stopping point here, go back and see if there are any specific questions. A lot of activity in the chat.
We've
Rob,
been having we've been having a great chat, Brandon, but no real questions have come up about your model.
Perfect. Okay. Thanks, Rob. Appreciate it. So what we can do now is maybe move away from these elliptical cross sections and give it a little bit different shape. So let's start with the fuselage. Let's come back to our wireframe view, and let's start to adjust some of this stuff. So maybe we think that our people are a little too high in that fuselage, and we want to get them away from some of that structure. Okay? Well, the first thing that we'll want to do is set them a little bit lower. Let's go to a left-hand view, bring them down just a little bit. Okay, maybe something like that. So now, unfortunately, we've got some feet sticking out down here at the bottom. So again, if we had a shaded view, it's pretty easy to see on both of these. Let's shade both. So, okay, yep, we've got feet and toes sticking out the bottom of the fuselage. That's no good. So let's go ahead and adjust this cross-section on the fuselage. Cross-section 1. And we're going to change it to something different. We could do a rounded rectangle. So we pop that in there. It's got a default setting for the rounded corners. All the feet are inside, great, but that's kind of boxy. That might not really be what we're looking for. Maybe we adjust the radius a little bit. Okay, not so bad. But it might be a little bit straight-sided. We can do a little bit better, I think. So instead of a rounded rectangle, let's go to a general fuselage section. Again, it reverts back to an ellipse. That's totally fine. But we're going to play around with some of these tangent strengths. So you're getting a little bit of a demo into cross sections and how to manipulate them in OpenVSP, but it's relevant to the problem that we have, because we have a lot of room here on the side to try and account for where these toes and the feet and everybody are. We don't need that. So let's cut back on the size of this fuselage. If we come down to our bottom strength, you can see that that's just pushing this out some. We can also push out from the lower side. So here we've pushed out maybe a little bit farther than we really needed to. Let's change this to maybe 1 and change our bottom to 1. That wasn't quite enough. Let's push this out a little bit more. Great. So if we set something like 1.5, that's a little better. Great. So on the top, we can either leave it as is, we can make it a little bit more boxy, but it's probably okay for what we're trying to do, because we really just want to leave room for the feet, bring this in a little bit, and then have a nice shape to give everybody some headroom. So we can probably dial our width back a little bit to something like that. And again, it doesn't look like anyone's feet are actually touching. There's another handy little trick if we want to do a fun feature. So let's go and check out Snap To. Now, this is one of those features that it's not really on the agenda today, but we can demonstrate it here. If we want to do a minimum distance, let's say we want to give them a little bit of clearance on their foot. somewhere in the neighborhood of a little over an inch. Why not? If we were to take the width and drag this down, now we have the manual collision detection. And what this will do is it allows us to manipulate this variable until it hits something. So if we try and decrease the width, you can say, nope, can't do that. We've already got intersections back here. That's not what we want. But we can come back to this other cross section. In fact, why don't we just copy this one for the time being, paste it back here. So everybody should be inside. Now let's see if we can decrease. Not one to play ball. That's fine. So we can't check clearance. It's saying that it's not touching. Anyway. So if we start to play around with these, we can adjust our settings. Let's go back to cross-section 1. So we've been able to cut back on the width. You can see about right there, things poke through. So let's make this only about 5 feet wide. Seem to have some good clearance. Everything looks great. Wonderful. We can copy this, and since we picked 5 for the beginning, we'll pick 5 for this one. That may still be a little big, but we made something that's a bit more fuselage shaped. All right, so we got a little bit of refinement out there. Now we can come in and play around with the wing a little bit. So in the wing, by default, the airfoil that we've picked is just a simple NACA 4 series. In this case, it's a 10. If we want it to be something different, we have a whole list of different cross-section and airfoil types that we can pick from. Just for fun, we can set that to a 6 series. We can even pick what flavor of 6 series you like. So we can do something like a 64A, adjust the thickness to chord ratio up to something like, that's down here at the root. Let's make it kind of beefy for some structure, 0.15. Great. So we've adjusted that. We can again copy this, paste it out at the wingtip, but we don't need it to be quite as thick out there. So let's go down to, say, a 10% airfoil. Great. OpenVSP is taking that root airfoil that we set down here and interpolating the sections all the way out here to the end of the section at the wingtip. All of that stuff is taken care of for you. Another thing that we can play with that I alluded to at the beginning of this demonstration is that we can define what the blades themselves look like. So as an example, let's pick these inboard, change that back to blade mode. And here we have just a regular shape. Again, there's not a whole lot of wireframe density in this, but if we crank it up, there we start to get something that's a bit more representative of the shape that you see in the curve. You can back that down quite a lot. If we want, we can come to the blade tab, and here we have complete control over the chord, the twist, rake and sweep, skew, all sorts of stuff, the thickness distribution and the ideal lift coefficient. The prop component treats these as continuous curves as opposed to hard cross sections like you would get with a wing. So because we have a cross section or an airfoil that is an ellipse at the root, it turns into a 1/6 series right here at about 0.4 of the radius, and that 1/6 carries on out here at the tip, and it's very, very thin. You can see thickness scored is only 3%. We can adjust that. Let's say, for example, that our propeller needs to be a little bit stiffer out at the tip. We can change the thickness, and instead of a cubic Bezier, we can change it to either linear, a spline, cubic Bezier, or approximate a cubic Bezier if you do something like read endpoints. For now, let's change this to a spline, and we're going to want to adjust this. So instead of 0.3 out here at the tip, let's give it, 8%. Why not? So we nudge that up. You can type the values in. You can also manually click and drag if you want. We can also delete a point. If that doesn't make any sense, we can just get rid of it. All right. So now you can see that as we're playing around with each of these, we have the ability to manipulate the model however we want. And the model is updating every time we let this go. It's bumping up and doing its thing. There we go. All right. So under cross-section, if we wanted to change that, again, we pick whatever airfoil we like. If we go back to the blade tab, let's say we wanted to change the twist distribution. Again, it's just a continuous curve. We can manipulate however we want. Same thing with the chord. Now chord here, move one of these, its adjacent control points move along with it. So the tangency is maintained however you move this thing around. And as I move it, as I let go, as I change things, the blade profile is updating. So I can shrink this down a little bit. Make it a little more rounded at the tip. Okay. So you get the idea. This is how you can come in and define your blade parameters. Now, it didn't update it for everything. It only updated it for that one. When you set up your model, if you want to link all this stuff together and make everything update based on a single parent or a single representative piece, you can do that. That's going to be a demonstration later in the week where we talk about links and advanced links, and we can show you more of how that works. But for the time being, let's just have an overall look at our tilt-wing aircraft. We'll give it all the resolution it needs. We'll have a look at our propellers in blade mode. All right. So again, here we've got a tilt-wing aircraft, 5 bladed rotors, 6 on the front, 2 in the back. Everything can be manipulated. Everything is able to be articulated. You can change and update the design parameters however you like on the fly. Nears makes no difference instantaneously. In traditional CAD, something like this would be a monumental effort without intentionally going in and putting the connections in yourself. OpenVSP does this stuff in a very user-friendly way, so that here, as we've just shown, in less than an hour, you can put together a fairly complex aircraft that articulates, moves, is sized based on any number of things. If you want to go in and change the design variables to be something like disc loading, thrust, your wing loading, what's your gross weight, all of that stuff can also be done. But you don't have to go in and change individual components and then rebuild everything and hope nothing broke. It all still works. They're all individual watertight geometries. This whole thing will mesh. The whole thing is closed. And so that is never really going to be a problem for you if you do things this way. So we've got about 7 minutes or so left here. And I hesitate to do it, but maybe it'd be kind of fun. Let's pop things back to a disk mode. Watch me crash it right here at the end after I spoke too soon and everything was looking really good. Yep, there it goes. Ha, I knew I'd get one. All right, well, we saved, so everything's fine. Here we go. All right, so first crash of the workshop. We got it out of the way, great. Oh, it doesn't like that at all. Second crash. All right. Let's try this again. All right. So this will be a slightly different version of what we just made. This is one that I made ahead of time just in case everything crashed. Lo and behold, it did. Great. So what we should be able to do now is play around with some of the analyses. Now, we don't really need the humans anywhere in here. That's fine. Let's go ahead and have a look at sets. Now, in this case, if we just pick set 0, let's say we want the fuselage, we want the wing, vertical tail, horizontal tail, and we want all of the propellers. Great. So if we were to come in and choose set 0 and show only, the people are gone, the hinge is gone, everything is where it should be. Cool. In any analysis, you can choose what set you want to look at. So in this case, instead of shown, we're going to use set 0. We don't bother with subsurfaces here, and we'll execute. So all this did was did an intersected triangulated mesh on all of the components. You can see that the fuselage and the wing are stitched together. It clipped, did the intersection, everything's good. And again, this is a watertight geometry. We can shade this. Everything's put together, even the disks. Let's get rid of that. Show only again. And if we do a quick look at what's the old version of VSP Aero now, if we choose that we want to play around with set 0, we can turn on our actuator disks. Okay, so everything is set to the defaults. Why not? We're going to do one run, leave everything effectively the same. Not going to play around with it. So let's just see what happens. This may not be a reasonable analysis, but let's launch the solver and see what happens. Okay, and we're done. So really quick analysis. We did no sweep. You've got CP distribution on your individual components. It shows you the convergence. But for the sake of the final bit of demonstration here, we can launch our viewer, which I'm going to bring up and show you here. So everything was included as a VLM. It collapsed the fuselage down to essentially a cruciform body. We've got some intersections in there that we probably shouldn't have. Okay, so I need to get rid of that and try this again. Let's launch viewer one more time. All right, it's popping up on my other screen. I'm going to do this here and then just pop up the display for you. Got rotors and nozzles. Okay, so I'm going to bring this up here. Good, it resized. So now we've got an aerodynamic solution. We've got our wakes. Everything's getting wrapped up. The rotors are displayed. It even indicates your turning direction. There will be more demonstrations of VSP Aero, especially the new features in VSP Aero this week. But for something like a tilt wing, it's really easy to set up one of these analyses. Now, again, you have to be careful, garbage in, garbage out with any analysis, but it's kind of made easy for you. That doesn't absolve you of responsibility. You still need to know what you're doing. But, I mean, what more could you ask for? This is pretty great. So we are coming up to about 12:30. That's going to be our first break of the day, I think. And then after that, we're going to come back with a presentation on three-dimensional cross-sections or three-dimensional backgrounds. So Rob, is there anything that I'm missing in the chat, just kind of last minute that we want to show people, or are we pretty much good to go here?
No, you've been doing great. I'm as puzzled by you about that crash that you saw. If you could send me that file that's crashing on Open, I'll see if I can figure anything out about it. Sorry about that. And no, we've been having a good conversation.
Great. So I see a lot of good stuff going on over here in the chat. I'll have a look at that while I'm on my break here. Again, this is kind of a notional model. I'm not going to release this particular version of it. I could. It might be easier to release, but since the OpenVSP representative UAM models are out for the Revolutionary Vertical Lift Technologies project, just go to the website and download that one, and then you can start from there and see if you can do better. That's kind of what they're for. But that concludes our tilt wing demo. I hope everybody enjoyed it. I hope it was informative. If you have questions, you're welcome to post anything either here in the chat or, as always, follow up with us on the OpenVSP Google group. We can post a link to that so that everybody knows where to go. But otherwise, we will see you all here in about half an hour. Okay, I'm going to discard all of this. Stop sharing. Okay. Let me see if I can get all this stuff sorted out first. All right, there we go. For everyone online, that is still tuning in, I'm just going to stop the stream for a little while. It's probably just going to hold on this screen. Um, in fact, I may just leave it here. I'm just going to mute everything, but we will rejoin you here at 1 o'clock Eastern Time. Move this out of the way. So for everybody online, we're just getting ready to come back from the break. There was a question online, and Rob is going to do a quick demo here. So Rob, you are welcome to go ahead.
Thanks, Brandon. So we've had a question about how to make a chamfered cylinder, and so I'm going to try and do that real quick with a stack. So this has been in the forum. So this is the stack component, which is just a stack of cross sections, and so it's really easy to do, assuming I understand what they mean by a chamfered cylinder. The tricky part is you have to turn off skinning. So to turn off skinning, we come to the skinning tab on the stack, and we control it on a per cross-section basis. This won't be a full deep dive on it, but we want the symmetry all the way around. We want the same. We want to turn off setting both sides equal, and then we want to turn off setting them at all. So those are the steps you take to turn off skinning at one cross-section. And then unfortunately, we have to go and do this all the way through. So then we go to the next cross-section, turn on symmetry, turn off equals, turn off set. Go to the next cross-section, symmetry equals set. Next section, symmetry equals set. And final cross-section, symmetry, turn off equals, and set. So now skinning is off, and so it's just going to be straight line lofting between sections. We'll come back. The first cross-section is a point. All the way to the beginning, that's a point. So we'll go to the next one. Since we wanted a cylinder, I'll make it a circle. We'll just make it a diameter of 1. And we'll go to the next one, and we'll make it a circle, and we'll make it a diameter of 1. And we'll go to the next cross section, and we'll delete that one. And so now we have, something that, depending on your definition, is starting to look like a chamfered cylinder. We've chamfered all the way to a point. Those aren't 45 degrees. So now what we want is we have a diameter of 1, but the distance in x, the delta x between the point and that is 1. So if we make that equal to the radius, we'll make that 0.5. Now at least it's 45 degrees, which still may not be what they mean by a chamfer. So next what we'll do is we'll come back to this point and we'll say, okay, let's make it a circle as well, and say we'll increase its diameter to 0.5. Why not? And then we'll know that the change, if this is 0.5 and this goes to 1, then the change in radius there is 0.5. So I think to make that work, we need there we go, that's a 45. So we created that chamfer on the front. With the problem, since we made the front an open surface, we made it open. So we can either go back and insert a point and make it insert a cross section, make it a point, or we can go to the design tab and we can change the nose cap type to flat. And so that will close off that nose cap. We could also do something like put on a round button nose, which will make it a portion of a sphere. But the easiest thing there is to just make it flat. And so that's how I would make a chamfered cylinder. Let me check the comments here to see where we stand. So hopefully, Keith, that answers your question there. So Daniel, unfortunately, we've had a question about clustering along the fuselage, and it can jump at cross sections. Mostly the jump comes in when you have a significant change in strength before and after the cross section. So if you change the tangent strength before and after, that can really throw your spacing off. If your spacing is the same on the top, bottom, left, right curves, sort of circumferentially around, you can actually use the clustering in inverse proportion to the tangent strength jump to get a uniform spacing. So that's a nice trick, is that if you have, say, let's just come in here and we'll have to turn cross skinning back on, but let's say we're at this section and let's turn it on the left, and we're going to change the strength here something, we'll make it really, really small so that we have, very non-uniform spacing. And on the other side, we'll set it there and we'll make that strength very, very big. So we have, really, really non-uniform spacing at this jump, what I can do, and I'm going to make it round numbers just so it's easier to deal with. So we'll make it 0.25. And so we also have the difference in X that we're also dealing with. But what you can do is you can come back in here to this cross section, and on now we're dealing with this section, and so we can change the clustering. That's on the forward side. Let's leave that at 1. But since this one was 4 times as much, what we can do is we can set this clustering to 4, and that will do what it can to try and make this more uniform. And you'll notice the first and the last are the same. So we can try and adjust some of that out. We can go to the next cross section, and now we're on this one. And so the before, if we change its forward clustering to 0.1, again, the inverse of what we had before. Maybe that's too much. Maybe I'm off on that. But you can see that you can use the clustering sort of inversely to the tangent strength to try and adjust that spacing. So we don't have a full-blown structured mesh generator that can do much more than that. Brandon, I'm going to turn it back over to you. Hopefully that helped.
Sounds good. Thanks, Rob. So for everyone online, just a reminder, we are getting set up to do some 3D background stuff. So this is always kind of a neat feature. It was long requested to be able to do this. So we're going to pop up just a brief presentation about 3D backgrounds, and then we'll do a live demo because I've already got something pulled up for you. So let me go ahead and hide my stuff, and I will bring up the presentation here. So see if this actually works. Great. So hopefully everybody can see what's going on online. And here we go. Okay. So again, OpenVSP has had the ability to display a background image essentially in the window itself to help guide the creation of the model, but it was up to you to try and set, say, the zoom, the panning, centering everything up, and forcing everything to be locked and keep everything relative to your model. And so it was very useful. You could certainly do it, and it was a great feature, but it had some drawbacks, and it's that the background images themselves didn't exist essentially with the model in 3D space. It was just a rendered image in the workspace behind everything else that was going on. So to address this, 3D backgrounds were implemented, I guess a couple years ago. Gosh, it was maybe 3 years ago. Too far. My apologies. Let me step back. So the workflow here is that within the window itself, you're going to choose the image that you want. You can control the display of it, so the transparency of the image, flip it, rotate it, make sure that everything is oriented relative to your model. You can choose the 2D reference point in the image itself. So you can see this kind of point right here that tells you where you are relative to this background image. You can also set the 3D position. So whether you're top view, front view, side view, where that is in the model itself, as well as the orientation, and you can scale it and set everything up the way that you want it to be. So the way to introduce kind of the GUI or the user interface that we will look at here in just a while, if you bring up the background 3D window, you can add, delete, show, hide, all of that from up here in this main 3D background window. The image itself, you get to choose by clicking Browse, and it will tell you the file path and what one you're actually working on. And you can also preview this image, so it will bring up a small 2D render of the image itself. Modify it so you can rotate, set the transparency, flip left and right, up, down locations, change the reference point, change when and how everything is visible, choose the orientation of this. And so this is kind of where you're aligning it with the rest of the model. And down below here, you can choose to either have a default view based on, say, OpenVSP standard view of top, left, front, back, whatever, or you can set up essentially your vector and you can point it off at different directions. The scale, you can choose which of these parameters that you want to use, including the resolution of your model or your image. and then the placement within the model itself. And so a lot of this will make more sense when we get to the demo side of things, but this is just an overlay of the user interface itself. So again, as with many new features in OpenVSP, it has been added into the API. So this is an example of some of the calls and functions that you can use in order to set backgrounds. So for example, showing all the backgrounds, getting the relative paths so that you can set that stuff. Now, the relative paths are relative to your VSP3 model. It's not relative to, your VSP home or your working directory, anything like that. So if the model hasn't been saved, the paths are completely meaningless. It has no point of reference to move on from there. And so, as promised, that was short and sweet. I'm going to go ahead and exit out of the presentation here and bring up some of my other windows. And while we're at it, if there are any questions in the chat, Rob is responding live, or if there's a question that I can answer, I'm happy to do so. But let me go ahead and bring up OpenVSP, and then we can go ahead and proceed with a live demo. All right. So just for fun, as I guess a preliminary, we're going to open one of the examples that we've got. So let's go straight to this, and we're going to look at, in this case, notional Boeing 737-800 with 3D backgrounds in it. And so you'll notice that because I loaded this in and I moved the file, all of these that I had set up, now it has no idea where the images are. So it just renders them black. So we're going to fix that. We're going to come to Model. Actually, we're going to go to Window. We're going to come to 3D Background. And so here we've got that user interface. So the top view, here we've got images, etc., etc. So we're going to browse for that. We need to come and try and find this. So what I'm going to do is I'm going to come back. I have too many favorites. I'm going to go into here, example aircraft, nope, tutorial models. Here we go. So in this case, we're doing our top view. Okay, we'll have to fix that. Our side view, we're going to browse for that one here. Okay, and our front view, again, browse, we're going to pick our front view, accept. Now, you'll notice that even though we have these loaded in here, things are in a bit of a different orientation than I really meant them to be. So let's start with the top view. We're going to move that off. You know what? I'm just going to turn off the visibility on the side and the front. Okay. So notice that if we have our top view here, it's confused. It thinks that it's supposed to be left aligned. Well, we don't want that. We want it to be the top view. Okay. So at least now we're looking essentially in the same plane. Great. But it's rotated. It's kind of in the wrong spot. It's probably a little bit in the wrong scale. So we're going to go to our rotate. We're just going to do a 90-degree clockwise rotation. Great. And again, here's that preview button. So there's that center that you can see right there. So relative to what we have, you note that that would be right down here somewhere. So because we have on our top view, the horizontal is set to left, vertical is in the middle. What we'd rather have, I think, is that the vertical or the horizontal should be center, and the vertical then should probably be in the top. So now our reference is right up here on the nose. Now that's getting us pretty close to what we want. Now the trick, now that we have that set up, is to make sure that our scale is appropriate. So you notice that this happens to be pulled from a essentially an airport planning document that has a few aircraft. It shows you notional dimensions on everything. That's what I used for this example in the OpenVSP Ground School. So in this case, we can adjust the scale of this model by trimming this down. So again here, this is where this range is going to help us quite a lot, because we need to shrink this down. So if we blow it up just a little bit, we can start to line these things up, and that looks pretty good. Now the great thing about this is I can zoom, I can pan, I can do whatever I want, and that background moves with this model. So gone are the days where you had to fix your aircraft on a screen and snap it to it and save the view, or otherwise you were completely hosed and you had to do that again. It stays put, and it's a really handy feature. So I think instead of our placement that we have there, we know we kind of need it to be nudged back just a little bit, and we might need to move that a little bit in Y. Now again, the directions here are in your model coordinate system. So X, Y, and then Z is up, down. So we can play around with some of our scale and get everything just right. So now we have our aircraft, and all of this is essentially set up. Because the depth here is set to free, I can move this around wherever I want. I can set it up high, I can put it way down below, I can set it kind of smack in the middle of the model if I want, and set this to 0. Doesn't really matter. So another really handy thing with these 3D backgrounds is if this is cumbersome and it's messy and you can't see your aircraft when you're looking at it at an angle like this, well, that's not really what you want. So why don't we change with some of the visibility? So instead of seeing both sides, we turn that off, and it's only visible when it's essentially in the positive orientation. So from the top down, you can see it, and it turns off from the bottom. Pretty cool. But let's take this a step further. What if we only wanted to see this when we were within, say, 5 degrees of the top view? So now, if we rotate off of that particular view, and again, this is just 5 degrees off from essentially the z-axis or the normal vector here. So if you're aligned in a top-down view, it pops up, it shows you where you are. If I rotate, change this view at all, it disappears. It doesn't change, it doesn't move the path, everything is right where it is, and it continues to move with your model. It is only visible whenever you are in an appropriate orientation to make use of that cross-section. So really, really powerful capabilities here when you're trying to build up against, say, a 3-view drawing, photographs, you name it. So because we can essentially set the placement or the direction at any direction, any angle, any scale, if you have a picture of an aircraft and you know that it happens to be at this weird angle, sure, put that as your background, orient it relative to that angle, and then you can size your aircraft as if you were looking straight through the wireframe at the background image. And again, it moves with it. So really, really cool stuff here. So I'm going to turn that off and leave both sides. So here we've got this one kind of floating around. The side, same thing. We're going to turn the visibility on, but it's clearly very confused. It thinks it's a top view, when really we want that to be a left view. We're going to turn off or disable that rotation there. Okay, we're going to jump to a left-hand view and make sure we can align everything. With our preview button, once again, we see that it thinks that the center of this is over here. That's not really what we want. So let's set the center of this to the left and the vertical in the middle. That works just fine, I think. Now we're going to drag this back. Let's maybe set it to 0. Then we can go a little bit more negative. Line up the noses. Okay. Clearly we need to adjust the scale here. So we're going to up this a bit more. Nudge the nose. Bump the scale until we're just about where we need to be. Now again, this is all set to free. If we did something like before, notice that the Y is disabled. It turns it off completely. So before means that it places it some distance away from your model and it sends it all the way out here. If you set it to free, you can adjust where that is. Again, let's jump back to a side view here. So we need to nudge this up in Z so we can line our nose up. not too bad. And if we wanted to, we could adjust the scale just a little bit more, but you get the idea. So again, because we have this all set up, we can do the exact same thing, set the tolerance to, say, when aligned, 10 degrees. We come off of that, it disappears, we can set it back up, and it stays on. 10 degrees, as you can see, is an awful lot. That's probably more than you really want. Maybe 1 degree is probably better, but sometimes that's kind of hard to hit. It's really up to you. Let's snap to a left-hand view. Okay, so again, here we go. We've got that set up. Set this to free. If I want to, I can set this cross-section straight down the middle of the aircraft. So if I happen to come in here and I knew that line was there, well, maybe I need to nudge the height of my fuselage, or maybe I'm not really satisfied with where my vertical tail is hitting and I want to adjust that somewhat. All of this stuff, again, moves around with it. So if you have a pre-existing line drawing, images, again, exceptionally useful to have this. Same thing goes for the front view. That one happened to stick kind of where we wanted it. I left it way there in the back. We jumped to a front view for this aircraft. It scaled it, had all the parameters where it needed to be, so most things are still aligned. We can do the exact same thing, but we don't need to belabor the point. Everything's lined up, same controls, same placement. Everything else just kind of works. So that is an example of 3D cross sections, and I'm going to save that just in case it completely forgets where those files go. Let's see. Not seeing any updates in the chat. Rob, has anything popped up that we need to address in the meantime here? Or is there anything else you'd like to show?
I haven't seen any questions about this capability, and I think you did a really nice demo of it. Yeah, I think you covered it.
Okay. Well,
that puts us a little bit ahead of schedule. I don't think we want to jump ahead of schedule, so I think we can just wait for the next talk to start at 10:30. If you don't have, yeah, I guess you could open up a different model, but that had 3D backgrounds if you had one ready. But otherwise, I think you're good to go.
Okay. Well, and stuff like this usually happens in a live workshop. We'll either, have a little breakout session or talk to folks. The chat seems to be doing a really good job with that. If there are, short demonstrations or little things that maybe didn't make it into the agenda that we want to just do a quick demo of to have on the record, we can certainly do that. And if you have something that you'd like to see, just please post it in the chat, let us know, and we can do let's see, is there a way to rotate the image with a custom angle? Yes. So let's take this front view as an example, let's say. Instead of these standard definitions, let's choose other. Okay, so it picked it up, but notice that as soon as I did that, the X normal flipped. Okay, so we can pick some other directions here. So now my X normal is 1. If I want to change that somehow, let's say I want to rotate it around. So now I'm changing the Y normal. I'm picking the vector that I want to use. So here we've got it pretty much at a 45 degree. And again, we can set this to any XYZ vector as its reference here. And so you can also, of course, rotate these. So this is, X rotation, Y, Z rotation. You're rotating, I think, kind of about these axes. So if we, let's say, go back to 0 and 0 here, where we're mostly aligned, and here I've got the rotation's all kind of screwy. But let's settle these back to 0. So hopefully that answers your question. Yes, you can absolutely set. That was not what I wanted to do. I think I broke it.
If the question was about rotating the image in image space, kind of like that, the 90, 180, 270, then no, we don't have the ability to rotate the image in pixel coordinates in image space. Basically that decision was just made because we didn't want to duplicate the entire capabilities of Photoshop. We had to draw the line somewhere at user interface complexity and everything else. And so certainly it seemed like, being able to rotate 90, 180, 270 was going to be a very common use case. Every file is going to come in with a different orientation. But, being able to rotate an image 2.73 degrees was something that you need to do in Photoshop or GIMP.
All right, I'm trying to think. Let's see. We've got about 10 more minutes until the next presentation. Were there any other neat little features that we could demo that would be quick, that didn't make it into the agenda? There's probably hundreds of them. It's just a question of picking one. Let's see.
Brandon, if you open back up one of the NASA ones, the model you were doing during the UAM reference, if you could open up one that doesn't crash, open up the 5-bladed prop. I was going to ask you to show the non-uniform blade spacing, because that's one of my favorite relatively recent features.
Yeah, let's have a look at that. So I can do something. Oh gosh, I don't want to open up the whole one. All right, let's just do a quick. We'll do new and just start over that way. All right, so for this one, really good idea, Rob. Let's go ahead and pop this in here. So we're going to fit this in and set things to, let's say, a 5-bladed rotor. Okay. So it used to be that all of this was essentially uniform spacing. Quite a while ago now, Rob put in the ability to fold these back. So that stuff is going to be under the More tab. Now you can pick the location of this hinge axis. That's indicated by this axis and the turning direction here. But now you can do this as kind of a per blade. So if we decide that we're going to fold this back, say 100 degrees or 80 degrees, it folds all of them at once. Okay, so that'd be something a bit like, folding back a pusher prop or something like that. But what if, instead of that, let's set this back to 0. Let's turn this on its head. Okay, so now it's a helicopter rotor. So we're going to do 90-degree rotation. So now we've got our Z is up. Okay, and so now what would happen then if we chose to fold and we rotated our angle? Oops, sorry, that was the wrong one. So it's the azimuth and elevation that I'm trying to change. Not elevation. I need to set it up correctly to do this right. It's been a while. You all caught me while I was rusty. Okay. So let's zoom in, make sure this is all making some sense. Okay, yeah, let's set to, say, a -90. All right. So this one blade, if we come in and try and give it some rotation, if you're trying to stow helicopter blades, you want them to fold back. But here, they're all folding essentially radially symmetric. So that's not really what you want. If we turn this on, now each blade has its own angle setting. So for blade 1 here, if we decide we want a 90-degree fold, awesome. Blade 2, what if we wanted a 90-degree fold and then we take it a little farther? So we can make it fold 160, something like that. So for each of these blades, you can set it up for whatever custom fold angle that you want. Now, in this case, 180 is the maximum. Couldn't go that direction. What we really need is for it to switch around to the other side. Let's do -120 or something. Not too bad. So what's very handy is, instead of being able to come in here and set this manually each time, you can use modes or what I suppose used to be called variable presets, where you can say, I want the helicopter rotor blades to be in the stowed configuration. And that means that every single one of them with this angle setting points them in that direction, and that's where I want them. So you can adjust each and every one of these, and I think you can also independently set, oh, I could be wrong about that. Looks like the angle is unique, but the location of the hinge is not. Rob, is that accurate?
Yeah, they all share the same hinge, but the
Gotcha.
angle is all that's unique.
Okay, yeah.
Brandon,
So,
this is really cool. But the thing I was actually asking was the next box down, the blade spacing.
yeah, yeah, I'm getting to
Okay, you're
that.
getting there too.
Yeah, so we're going to set this back to 0, okay? And so let's jump to a top view. And so now, let's say that you wanted to have control of your blade spacing. So you've got uniform, free, or balanced. Now, let's pick free. Blade 1 is always blade 1. It's there, but for every other blade, notice that it's pre-populated with the location azimuthally around the rotor. So if we wanted to change where these blades are on the prop, we can adjust that manually. We can adjust that by a delta. So let's say we want it 10 degrees ahead of where it would otherwise be if it was evenly spaced. The other option that we have here is to move to a balanced option. What that does for us is it takes away control of some of the other rotors and it maintains balance relative to these other positions. So let's go back and set this to essentially 72 where it was. Now, if we know we want to adjust blade 2's position, you can see that the other two, essentially opposite, are adjusting with it to try and maintain essentially mass symmetry about the origin here. If we come and start to mess with blade 3, it's moving the others to try and maintain, again, mass symmetry about that point. So OpenVSP is doing this on the fly. We're not coming in and having to recalculate, well, where would this one be, and where would this one be, and where would this one be? It gives you control over the ones that are relevant and lets you set the spacing or the physical position so that you can have things like a non-uniform tonal signature and start dealing with destructive interference for acoustics or for rotor performance. Or if you've got, an even number of blades and you want to get rid of that really nasty 1 per rev, bypass frequency, adjust a couple of them and it balances it all out and keeps everything happy. Rob, any other little tidbits about these features? Did I miss anything?
No, that was perfect, Brandon.
Awesome. And a really, really cool set of features that if you need it, you're so happy you have it. And for a lot of people, they would never touch it. But because we make it so easy, it becomes exceptionally powerful, like a lot of stuff with OpenVSP. Let's see. Okay. So chat's still going strong. Thank Rob. We've got about 3 more minutes here. I think you're up next with routing geometry. Is that right?
Yep. And I'm ready to go. We'll just wait until the half hour.
All right. Sounds good. Let me go ahead and close this out and give my workstation a break. Oh, good. And it's doing my transcript. So I've got that going for me. Let's see. So let me get this out of the way so that everybody doesn't have to sit here and stare at my mug for the next 3 minutes. All right. Close that out. Move this to a different window. Shameless plug for the ground school, everybody. I can't even remember when I started doing the ground school. It might have even been back in like 2019 time frame. So it's been years. So anybody that has extensively used that training program probably knows my voice better than I do.
Yeah, I remember Cam saying that he hears your voice in his head when he uses VSP.
That's probably true for a lot of people these days. But I mean, that's kind of the point of it. I
Perhaps
can't
creepy,
tell you.
but
Well, it could be worse. Um, but I'm really really glad that everybody has been able to use that resource, for training in classrooms, to picking up on features to help with their designs, to any number of things. That's exactly why we did it, and I'm really glad that everybody has used it so much.
absolutely, absolutely. And I'm super glad that you did it.
Yeah, that was tough. Um, all right. So where are my little windows here? All right. So I think here we are. We're just about 1:30 or so, Rob. So whenever you're ready, you're welcome to go ahead and share your screen, and I'll get everything set up here for the stream.
Okay, I'm sharing and in presenter mode.
All righty.
Are we ready to go, Brandon? Okay. Well, thanks a lot, Brandon. I hope everybody is back ready to go. So routing geometry is a new feature that got added this past year. The presentation on it's pretty short, so we'll should have some nice time for a demo at the end, and certainly for questions along the way. So historically, OpenVSP components, the different geometry things, are each defined independently. Each, whether it's a pod or a wing or whatever it is, it's its own thing with its own parameters and its own position, and it's not dependent on the other parameters. Um, and so there's some exceptions. We can use attachment to build positional relationships between components. So attachment doesn't change the shape of a component, but it changes its position and orientation relative to its parent. We have conformal components. We haven't talked about those yet, but a conformal component builds its shape off of its parent component. So typically you'll do an offset thickness. So maybe you want to model a fuel tank within a wing. And so those use the parent shape, but they use directly the immediate parent's shape. And then there's also what we call subsurfaces, which is the ability to sort of draw a box or a line or some curve on another surface. So you can draw a control surface on a wing or draw a window on a fuselage. And therefore, obviously, the window shape is dependent on the shape of the fuselage. But in all these cases, the dependence follows the parent-child lines. And what I mean by that, when we look at a model in the Geom browser, we see this hierarchy where as we go down the tree, in this case, the fuselage of this model has a child of the pilot in the cargo bay, and also the horizontal tail and the wing. The horizontal tail has the vertical tail upper and lower as children. The wing pivot has the wing as a child, and then a cell tilt, and all these all the way down. And so all of these different components are parent-children. And so the way attachment is identified is this sort of this double bold line indicates that the wing is, well, forced attached to the wing pivot, or the vertical tail is attached to the horizontal tail. So here we represent attachment with these double bold lines. But the way information works in an update of VSP is, for example, when you update the fuselage, then when VSP is done updating the fuselage, it then updates all of fuselage's children. And it checks to see if they need an update. It obviously stops if things don't need to be updated anymore. But we follow this hierarchy from parent to child in the update process. And that was a fundamental thing that was going on. Now, what this means is that, for example, you can't have a spinner over here. Well, no, that's not a good example. Let's say, no, we can't have the spinner and have the spinner's position or parameters depend on the upper part of the vertical tail, because it's not in that same hierarchy. You can't have the spinner and tell it to be symmetrical about the upper part of the vertical tail because of the way this model is constructed. And this limitation hasn't really been a problem so far, and VSP gets a lot of efficiency out of this approach. And so so that's been a fundamental design decision. What we're talking about now, routing geometry, kind of breaks that, in that we needed to find a different way. And you'll notice in this model, the routing geometry is not a child of anything else. And yet we'll talk about what it does and how it works. It does depend on lots of these other components. So the routing geometry is kind of breaking the rules of how OpenVSP updates things. And it really only matters right now for routing geometry, but it might matter more for other things in the future. So we'll have to keep an eye out to see what this means. So the use case of routing geometry, what I mean is we've got this sort of generic tilt rotor model here on the left that looks like a V22, but it isn't really a V22. And what you'll see, it's a little tough to see, but in here there's this black line that starts at one of the spinners and runs back the nacelle to the tip of the wing, to the root of the wing, down into the fuselage, and then back to the aft fuselage. And I've isolated just that line over here on the right. And so that is this routing geometry. This, zigzag line can be used to represent lots of things in an aircraft that are routed through the aircraft. So that includes, obviously, things like hydraulics, pneumatics, shafts, electrical cables, push rods, fuel lines, any of these kinds of systems that are routed through a geometry, through an aircraft, is the use case for routing geometry. And back to that update hierarchy, a routing geometry can depend on multiple components, so it's not just single dependence, but it can also depend on components that are not its ancestors. So we have to break those rules. And in this case, you'll see that the routing geometry is attached to the spinner and attached to the nacelle and then to the wing and the wing root and then into the fuselage. So that routing geometry actually depends on half the components in this model. So it has multiple components that it depends on, and these components are not all in a linear, clean hierarchy tree. They're located all over, or potentially they can be located all over this hierarchy. There are limitations right now, and we may continue to improve routing geometry going forward. But right now, it is not a full surface. It's not an elaborate geometry. It is just a line representation. All of the joints, the corners, are sharp corners. So we're specifying it as like a 3D polyline. And we don't have the ability to put in a radius or a blend right now. And there's no cross-section shape. It doesn't have any area or any shape to it other than it's just a line. It's not a full first-class component. I don't generate a Bezier surface of this, and it's ignored by most analyses in VSP. It's also ignored by most exports. So if you build a routing geometry in VSP and you export to step and you take that into CAD, it's not going to go with it. Right now, it just only exists in VSP. And then back to that update hierarchy, you can't attach something to a routing geom. You can imagine that if somebody routed something through a model and then they attach something to the routing geom, that would create the potential for a circular loop. And infinite loops are bad. So to prevent that, we just made it so that you can't actually attach something to the routing. You can only attach the routing to other things. And these are the current limitations. That's just the ground rules that you have to work with if you want to use this. But what it does give you the ability is to visualize this route, whatever this is, whether it's a fuel line or hydraulic or a shaft. You can visualize what it looks like through the aircraft, and it'll also calculate the length. And in the current example, this is actually one routing component, which was built up on the right wing, and then it was mirrored using symmetry to the left wing. Down the center line, they're coincident, so you can't see them separate. But when it calculates the length, it calculates the length of just the first copy. And then if there's 2 symmetrical copies or 3 or 5 or however many symmetrical copies there are in your model, it'll then take that length of 1 and multiply it by the number of symmetry to give you the total length, if that's what you need. And so for most of these things, say it's wiring, you could use this to do a hand calculation of the mass of that wire, because you would know that for whatever gauge wiring you have and however many strands, you would be able to say, okay, my wiring weighs this much per foot or this much per inch or this much per meter. And you'd be able to take that length calculation and get at least a first cut mass properties calculation. If it's pneumatics and you're doing a loss calculation, you'd know the length of that length, so you'd be able to do that loss calculation. Again, if it's wiring and you're doing a resistance calculation, you know the gauge of your wire, you'd be able to then figure out the resistance of that wire. So all those analyses start with length, and we're really just sort of giving you enough to get started. Okay. So here's the routing geometry GUI. It's a regular GUI. It's a regular geom in terms of the general and X-form and mass tabs, although a lot of that stuff doesn't work in the traditional way. But really everything happens under the design tab. And up here at the top of the design tab, you have a GUI for interacting with each of these points along the polyline. So I'll call that the routing point chooser. And here I didn't give them names, but you can see each one is attached to a different parent into that symmetrical copy. And you also have these ordering controls. So if you need to change the order of points, you can click on one of these and move it up and down in the ordering. We have a bunch of buttons for point management, so you can add and insert, delete, or reset points, and I'll demo all of those in a moment. You can also name each point, which I was too lazy to do here, but you can name each point so that you can know that, you know, the endpoint is a battery terminal and the other endpoint is the motor, and you can name the waypoints to make it easier to work with your model. Then you can control the parentage. Now, when we build this, you can actually do it just by clicking on the model, and so parentage will be set automatically. But if you want to come in and change it later, you can come in here to these menus and you can change what a component is attached to, or what one of these waypoints in the routing point is attached to. Then you have full control over the attachment. So Brandon talked about attachment in the earlier demo, but you can attach a routing point in UW, you can attach it in RST, you can attach it in LMN, dimensionally or non-dimensionally. On a wing, you can use ADA. So you have all of these different ways of attaching it that should match, you know, your use case. When you initially attach things by clicking on points, and I'll demo this in a minute, the default is everything attaches in UW, so it'll be on the surface. And then if you want it to be within the volume of something, you can then change it from UW to RST or LMN, and then adjust that T component to put it somewhere in the middle. You don't just attach it, you can actually then offset it. So when you attach something in, you know, UV, if you then want to offset it, say in the normal direction to the skin at that local UV, you can come in and dial in a delta for that offset. So you have a tremendous amount of control of where the points are, either on a surface, within a volume, or offset in that way. And then down at the bottom is that length calculation I was talking about, where length is the length of the single copy, in this case 662, and the symmetrical length then gets both halves because we're multiplying this one by 2. And that's all for the slides. I can take questions in the YouTube chat while I fire up a demo to just show you guys how this works in practice. And some of the things I'll be demoing later in the workshop are not yet publicly released, but routing geometry is. So you can do this in VSP that you've downloaded. So to start with, let me just add a pod as just a quick demo, and I'll move that out and I'll make a symmetrical copy. So we have now 2 pods here, and then let's just add a wing, and let's move that up in Z, and we'll move it aft a little bit like that. So here's, just a very, who knows what this is? Maybe those are the floats on an airplane, and we want to build up some sort of a truss framework. Why not? So we can come in and, these two are related to each other. We could even come in and we can attach them. That doesn't matter. But independent of that, we'll come and we'll add a routing geom. So that's down the last one of these capitalized built-in components. And so we'll add that routing geom, and here it is. We'll come over to the design tab, and we can come and we can add a single routing point, right? There's nothing there yet. We need to add a point, and presumably we'll need more than one. So we might go straight to add multiple. And so when we add multiple, you'll see all these green dots appear, and these are the points that we can choose to route between. So we'll start and we'll route between this point here and up to here on the wing. We zoom in a little bit to say there on the wing, and we'll go back down to our fuselage or our float, and we'll click there, and then we'll go up again to the wing, and we'll click here. So there we just routed and we clicked, 3 points. We're now still dangling around to add more, but I can just come over here and click stop adding, and I'm done. And so right there, I've created a routing geometry between 1, 2, 3, 4 points on this wing. And the great thing is that if I come in here to the pod and I move that pod around, you'll see the routing geometry is updated on the fly, where I can come into that wing and I can come in and I can change the sweep angle on that wing, and I can do anything you want. I can update the tip chord on that wing, and everything's updating on the fly in that routing geometry. And if I come back, you'll see we've calculated that the length of this is 26.77 units. If we want to turn on the symmetry of it, all we have to do is come up here and turn on the symmetry of that routing geometry. In this case, the symmetry is applied somewhere of its hierarchy. It's a base model, so we can really only be symmetrical about the global origin. And that gives us 2 of these things, so we can come back over to the length, and we'll see that their total length is double, as we would expect. Now, if we want, we can come in to any of these points, and we can change them. We'll come to the second point, which you'll see it's highlighted with this blue dot right up here. And if we don't like the way that is the place where that is attached, you can see we can come in and we can dial, leaving it in UV or UW. I can move that point of where it's attached, and I can move that along the surface because that's what UW does. But I can also come in and say, you know what, I want to change this to say eta mn, and it stays in the same place because we're calculating the equivalent coordinates in all these different systems on the fly. And so eta mn, eta is our span-wise coordinate, m is our chord-wise coordinate, and then n is our thickness coordinate through the volume. And so if we want that in the middle, we can just change that to 0.5. And now you'll see that as I move that in the m direction, which is the chord-wise direction, we're just moving there through the center of that wing in thickness along the chord, and eta is along the span. So we can change how that is done. We then have the ability to do this kind of, a delta in the coordinate system. which allows us to come in and we can then offset in each of these axes. You'll notice that this coordinate point has a triad. A red, green, blue triad is shown at that point, which is where the A to MN is attached. Let me change it back to 0 to convince you of that. So as I move this around, you'll notice the triad is moving with it. That triad tells you that local XYZ coordinate system that it's going to use if we put in some sort of a delta. And so, we can move that along that local XYZ. Or if we come back, you'll notice that when I switched to absolute, now we're in global XYZ instead of relative. So relative is actually moving in model units, but in the unit vector directions of A to MN, taken instantaneously at that point. Whereas if we go to absolute, now we're just moving in global XYZ from that point. So relative allows us to, say from A to MN. It makes a lot more sense. Let's say if we go back to UV, now we're on the surface, and let me move that so that we're somewhere up around the leading edge. You'll see that normal vector, that Z vector, the blue one, red, green, blue, the blue one is orthogonal to the surface there. So if we come in and we say, okay, we want to be at that point, but then we want to offset, a certain distance off of the surface in the local normal direction, that's what that delta is for. Okay, so you see we have a lot of capability to move those points around. If we come up and we say, you know what, I want to change what that was connected to, I can either come back to the parent and I can say, I want to instead connect that to, the pod or to the wing. I can change from surface 0 to surface 1. So that's the symmetrical copy we can attach over there. So we can change that, or we can come in and we can just say reset point. So if we're on one point, we can just say reset. It'll give us the green dots. Now we come back and we can pick where do we want to attach it to. So now let's say, we wanted to attach it out there, and we've recalculated everything. In addition to add, I added these initially, but if I want to add more, that's going to add them at the end. So it'll add it at the very end of the list, whether we add one or whether we add multiple. We can also insert. And so what insert will do is whichever one is selected, it will insert before that point. So if we have number 2 selected right now and we say insert, we're going to be able to then insert between the first and second point. So we can do that and say attach down there. So now we have those. I can of course delete that point because that was crazy. We don't want that. So we can delete, we can insert multiple. We can also reorder them. So right now this point is number 2, but I can reorder that to say be number 3 or number 4, and you can change whatever that order is, and the lines all update on the fly. I think that's most of the features demonstrated on a simple model. Let me open up that tilt wing just so that we can see something a little bit more realistic. Sorry, tilt rotor, not tilt wing. So here we go, and I will shade it. So here's that tilt rotor model, and I'll be using this tilt rotor model later for more demos. But here's the routing. We have 7 points that go from here on the spinner all the way back. And the nice thing I've done about this is when I'm going through a joint, through a hinge, I've actually attached them to the hinge. So you'll notice this one is attached to the nacelle tilt, and this one is attached to the wing pivot. And then the reason that's nice is I can come in here, for example, to the nacelle tilt, and I can rotate that nacelle, and I can dial that in. And because the routing geometry is going through that point as it goes through the articulation, in this case, the length of that routing geometry stays constant because it's going through that point. Whereas if I drew it to some other point and I skipped that, it would actually stretch. It would either stretch or shrink as you rotate things through that articulation. So you just have to think about how your model is built. And of course, we also in this one, we have the wing pivoting. And I've set up symmetry in this case. Well, there's something that looks ridiculous. I've built the symmetry in this case about the global XYZ axis, which means that the second routing geometry is reflected over and about XYZ, so it's absurd when it rotates. What I should have done is instead built it symmetrical about the wing or about the wing pivot. Now I should actually be able to change this. So let's see what we can do, because currently in VSP we have the ability, and Tim will talk about this later, to change the parent-child relationship without destroying or cutting and pasting. And we can do that with these two buttons. Again, Tim will talk about this later. But if I change this parentage to inside, it'll become a child of the wing pivot. So we'll do that once. And so now it's a child of the wing pivot. And if we look at symmetry, is symmetrical about that. I'm sorry, now it's a child of the fuselage, so let's make it again. Now it's a child of the wing pivot. Let's see, let's move that up just so that, nope, I was wrong. That made it a child of the horizontal tail. So let's promote that. Okay, now we're there. Now we're there. Okay, now we're a child of the wing pivot. And we want its symmetry to be, and I've got this all borked. We want its symmetry to be about the wing pivot. I don't know why the origin one is so messed up. This may be a bug that I need to go fix, folks. Yeah, I'm gonna back up on this and say that I need to go sort this out and get the positioning right on this one. Let's just change this back and pretend like this didn't happen for a minute. But let me sort that out. But I think in general, you guys get the ideas of routing geom and its use case and what you can do with it. Any questions on that?
So we haven't been seeing a whole lot of activity in the chat over the last one. Good walkthrough on this. Really interesting feature, and given all of the changes that you had to make under the hood to even make this feasible, I think it shows some interesting promise for things down the road. But yeah, I mean, this is a brand new thing, and so it's still a baby feature, but still really, really cool. So I appreciate the walkthrough and the demo, Rob.
My pleasure. My pleasure.
So I don't know if you can see it. Brian just asked if there is any reporting for the geometry, like mass properties. Is there a way to export a CSV of all routing lengths and lines and how they're attached or placed?
Yeah, I see that question. So right now the length is not hooked up into the mass properties calculation built into VSP. It's completely independent right now because this feature was just added on a pretty quick schedule. You can, through the API, access the XYZ global coordinates of all the routing points. So there isn't an export like a CSV or another manual export of that at this time. But if you need that information, you can, write a quick Angel script or write a Python script and, update your model, and then you can dump out the XYZ coordinates of all those routing points, and then you can do your own, calculations from there.
Let's see. So no other questions in the chat at the moment. We've got just a couple of minutes here before we jump to the next presentation. That's where I'm going to be walking through integrated flow path modeling using engines, fuselage and stack components. So we've got the presentation queued up for that and some demo models, and we'll be able to walk through that in just a moment. right, so everything should be set back up to record the next session of the presentation here. Clear out some of these notifications that keep popping up, even though I told them not to. All right, so it is 2 Eastern. We're going to go ahead and proceed with the next presentation here. This is on integrated flow path modeling. And so some of you have seen this in the live OpenVSP workshops before, but for everybody online and for those that don't have it yet, this will be a recorded presentation kind of walking through what the component is, what it's for, and a number of different ways to use it. Let me make sure, here we go. So why have this at all? So essentially this entire process, the point of these features is to simplify propulsive flow path modeling. And so that goes into some of those discussions that Rob gave all the way back at the welcome and the introduction as to, this has to do with geometry and it has to do with analysis. And there are many, many ways to model the geometry in your design. So in a sense, you could have several different things that represent, say, the flow path or the engine itself or the outer mold line or the cowling or whatever it is that you need. But ideally, you'd like to have a single representation and intent. So in this case, the geometry in every one of those conditions is built to suit that one thing. But if you have, say, a buried flow path, an engine that goes through an aircraft, well, now you have an inlet, but you also have the engine itself. You've got the nozzle. You have all this other stuff going on. So the goals of the flow path modeling is to maintain that flexibility that's kind of inherent in OpenVSP. It's to let you do what you need to do and get on with your life without having to keep track of all this other stuff. So the support here is really, how do we model these buried flow paths that go through an airplane or through a vehicle without losing the flexibility and what you need to show how it looks on the outside. So let's have a look a little bit at how you model the geometry and how you identify what it is that we're talking about here. So in a flow-through component, if you imagine these dashed lines here, let's see if, there we go. So control gives me my laser pointer. So a flow-through would be as if the geometry here is on the outside with, the inlet lip, the inlet face tag, an outlet face tag, and an outlet lip, and everything can flow straight through the inside. But if we're talking about the flow path, well, here the inlet, the flow path goes from the lip to the face, and it's this shaded region right here. If you're talking about the nozzle, the flow path is the area outside of all this stuff that happens inside. So here is your exit flow path. And if you're talking about both, the flow path is everything from the inlet lip to the outlet lip. It's this entire shaded region in the middle. On the other hand, if you want a geometric representation to include, everything goes on the inside, but you only care about the geometry up to a face. So in this case, the inlet is modeled right here to the inlet face. Let's pretend that this is a fan. So here, everything on the outer surface of the line comes back to the fan and stops. Same thing on the nozzle side. You start at the face, and then it goes out to the lip. On both sides, you can see this much easier. If everything comes in, you hit a face, you don't really care what's going on in here, and then here's the exit. Now, to close the geometry off entirely, if you only care of what's going on to the lip, you get this surface attached to that lip point, again, right there at the nose, and then similarly back here at the trailing edge of the nozzle. And on both, it just closes off the entire geometry from the front to the back. So that's the nomenclature that we're talking about when we are regarding things like flow through, flow path, to face, and to lip. So keep that in mind as we move on with the presentation and then later in the demonstrations. This will make a lot more sense. In the design tab of a stack or a fuselage, there's this engine definition section down here, and that's where all of this comes into play. So the model specification, you decide what type of geometry you're dealing with and then how you want to deal with it from, say, the inlet or the outlet. You also point to which section or U location on the model itself that you want to be the lip and the face of the inlet and the face and the lip of the outlet. And again, these are all color coordinated because you could get lost very, very quickly in OpenVSP geometries if these weren't tagged accordingly. So with this in mind, let's go ahead and have a look at what is the representation and intent of something like this. So with this similar shape that we've been using as an example, again, the dashed line here is our center line. If we want to extend beyond and essentially have the region fore and aft from inlet to exit, preceding and after this component, it extends a surface or extends the geometry fore and aft and just stretches it. Here we go again to the lip, to the faces, and flow through. Now, we also have these regions here where if we have a region to the face or even flow through, anything that is inside that we want intersected, we can treat as a negative volume. So there are prior OpenVSP demonstrations and discussions as to what a negative volume is for, what it does. But essentially, it's a negative Boolean where when it intersects, it says anything that is inside this, we're getting rid of. So when we do a demonstration, we can choose to have one of these things as negative, and it will clear out anything inside that region. That is down here in the engine representation side of things. So you can choose if it goes just, say, to the face, you can choose flow through, and you can decide whether or not it's going to be an extension, how far that distance goes, and if you want that to be negative. Part of the issue that makes this quite difficult is the U parameterization of the geometry changes with how you're representing it. So if we just have this shape here, if we start at the trailing edge, go around to the leading edge, and come back to the trailing edge, that's 0, 1, 2. 1.2 lives right there on the surface. However, if we change this to where it's to the lip and it closes everything else off, now we have 0, 1, 2, and 3. If we change it to face, it becomes a bigger problem. So now we have 0, 1, 2. 2.2 is now the location of that point. So the value has changed. And so as this becomes a different shape, as it becomes a more complex problem, where that point lives and where all these things are assigned can move. And so you can have things like fractional segments, and the number of U segments can change. Like all of this stuff is fixed. That becomes a problem for things like subsurfaces or probes, or as Rob just demonstrated, things that are attached in UW space, like a routing geom or any component that happens to be associated with this. So even though it seemed relatively straightforward to develop this component, there was a very long tail of unexpected consequences when you try and make this work and work well and be very reliable and robust. So it was a real challenge for Rob to get this going, but he did, and he did a wonderful job. So the base geometry modifications that we have here is to understand the difference between essentially coincident positive and negative faces. So that has to do with things like comp geom or CFD mesh. If you have a surface that is directly on top of another surface, then it crashes all sorts of stuff. It really cannot deal with that. Well, here where we've got essentially an interior volume based on everything that's the inside of this engine, and then what you can think of as the inner wall of the geometry itself, those are coincident surfaces. So what to do when those two are smack on top of each other? And so even if we had all of this stuff lined, any of these things, the tessellation that goes in between individual cross sections, attachment, hinges, structures like Brian Sandoz will do a demonstration of later this week, all of that stuff relies on not necessarily constant but well understood surface mapping. And when those things are changing on the fly, really bad things can happen. So all of that stuff had to be addressed in order to implement this properly. Other things that haven't quite been implemented yet are things like wave drag integration. So OpenVSP's Emerton load calculation and the wave drag solver that are in there. These flow through components are not necessarily a part of that. You still choose your inlet and outlet the same way you always have. It doesn't talk to the engine side of things here, the flow path modeling. The texture mapping under the hood has also not been updated to automatically update the U coordinate systems. And as well as anything that's based on automatic subsurface creation, that has not been tied into this for the time being. But it's mostly because those things were not very often asked for. So if it's something that you are specifically using, I'm sure we can find a workaround. But for now, these are the things that aren't necessarily integrated. So with that, we've got plenty of time here in the next 20 minutes or so to provide a demonstration. I've got a couple of models that we can pull open to have a look at how these things interact. But unless I don't see any questions over here in the chat, so I'm going to go ahead and exit out of this presentation and queue up OpenVSP. Rob, do you have any comments or little add-ons that you'd like to share while I'm kind of queuing things up here for everybody?
No, you're doing great, Brandon.
Perfect. Okay. Well, oh gosh, get that thing out of the way. There we go. All right, we're going to move you over here. Open some of my workshop examples. Okay, so the first one that we'll pull up is this engine test model. So this is just a whole slew of different representations of the engine component represented different ways. And so you should be able to see here online that each of them has essentially a check solid, or a piece that's a solid brick that passes straight through the middle of it. And so for each one of these, if we're looking at it, let's say flow path out. So in this case, we're only looking at the flow path from the outlet face to the outlet lip. That's all that's represented in here. So in the design, you can see the inlet is completely turned off. It's an outlet. We're using flow path. The indices coordinate to these cross sections are there, and the engine representation has been set. So that is that component. Same thing, you can have that for the inlet. Here, if we step ourselves down just a little bit, flow path, both. In this case, we have our flow path from the lip all the way through to the inlet face, outlet face, and the outlet lip. So that is the solid representation of the flow path on this particular geometry. As we move along, we wanted to see something a little bit different. Here down at the very bottom, let me close this geometry and just pick this one. And so here we have both. Everything has been closed off on the lip. We've got flow through, etc. So what I'd like to do, I'm going to leave this at both. Inlet type is flow through, and here I want to choose flow through. So in this case, we should be able to see straight through this geometry. So because we've set it to flow through, we've got everything set up on this engine. It just passes all the way through. If we do a comp geom test on this, which is just our intersection routine here, we're going to use all of our shown components, and as long as things don't crash out on me, here we go. So again, this check solid just shows that there are parts outside and inside each of these geometries, and anything that was exposed is there. So these check solids are passing through the geometry. Here's the outside.
You might shade or do a hidden view.
Yeah, I think I will, because it's a little tricky to see. Here we go. So this is essentially all the outer surfaces. Now, if we go back down here to the bottom, there's that one that I gave it a pass straight through the middle. Okay? So everything is passing through. Let's delete that. We're going to show and bring our models back. Okay, So here's this one again. We've got our flow through, but instead we're going to pick flow through negative. Now, note what happened. Flow through negative now closed off the front and the back of the engine, but you can still see the inside of it modeled as a flow through component. I have to get rid of that. It's annoying that it keeps popping up. So let's look at what happens if we do that again. So I'm going to go ahead and no show the rest of these because they're kind of irrelevant to this demonstration. And we're going to run compgeom again. So here, again, shown set, execute. And now, if we go to a hidden view, note the difference. Because we chose a negative component on this, everything that was inside this engine got cut out. So if you, for example, have a strut or a pylon or a wing or something that's passing through this geometry, and you treat that flow through as negative, the inside of that is going to cut it out. So that's a few different ways that you can manipulate this. Now, while we're on this particular demo, let's delete that out. We're going to show this component again. And let's have a look at each of these cross sections themselves. So I'm going to get rid of that flow through negative. I'm just going to make it flow through again. So in this geometry, you notice the cross sections, we're in a loop design policy that takes this cross section, loops it all the way around, and forces the first and last to be coincident. They must be at the same point. So we come all the way back to 0. That's us way back here. So in this case, we are positioned where the cross section is effectively 0. So if we step up in 1, okay, there's our cross section on the outside. We come back. Oh, I see, this is a stack. So we're actually looping from front to back and then back to front. So we're going out, we come back, we're moving here, here, and here. This would be a little easier to see if I had opened this up in 343.1 instead of the older version. But in any case, here we are, we've got control of these faces. So if we start to change some of these, note that the tag on the U surface is just the location. The surface can change, you can adjust the flow path, you can do whatever you want, and everything remains the same. That negative volume, everything associated with these, all adjust accordingly. So everything tracks. If we come back to design now, notice we're using the index of essentially cross-section 3 here, or as, it's cross-section 3, as the index. If we turn that off and say, well, rather, we'd like to pick U instead. So we're allowed to float the location of this somewhere else. Maybe we want our hard cross-section to be here, but really the face of this is somewhere down on the other side. Totally fine. So as we're moving this around, we can define either by the index of the cross-section or by the U location as it moves around the model. Again, if we change this and we wanted to say, well, the inlet is to the face, the outlet is to the face, great. Again, we can move this, and that face geometry, the volume inside, all of that automatically updates just wherever this outlet face happens to be. And so everything inside, you've told it, you don't care where that is or what it's doing. So that is essentially a simple example of where these things go. Now, as a quick demonstration, really, let's go back to index, leave it at index 3. Let's do something like, let's attach a blank to this, just to give you an idea of what's going on. So we're going to take a blank. We're going to add that as a child, okay, and we're going to set it in UW space, and we can leave the rotation alone, doesn't really matter. So again, we're at U equals 0. We can come all the way around. There's our first one, second one, and aha, see how it jumped and it went across. Now things are moving around. So things are behaving a little bit odd. But if everything is positioned the way that you want it to be, let's move and adjust this component. Here's our flow through, and instead of to face, we've got flow through. Now, notice what happened. If we go to face, the location of that point, its attachment on the geometry itself, it didn't move. It stayed right where it was supposed to be. Same thing here. We can say to lip. We can say to face negative. We can extend that. So if we extend it aft, that blank where it's attached in UV or UW space on this geometry does not move. And so that is essentially OpenVSP under the hood, figuring out how it needs to adjust that value to keep things attached so that things don't explode and get all tangled up anytime that you adjust the definition on this model. We've got about 10 more minutes here. So for flow path modeling, I wanted to show a bit more of a real world example of this. So this is an example of a model that I put together for the workshop in 2023, I think. The one in Dayton. It was a few years ago. But we did kind of a live build-up of an MQ28. And so a lot went into trying to make all these little features exactly right, and it was a bit of a pain. But it's a cool looking airplane, so I thought I'd use it for the demo here. So let's go ahead and shade this for starters. So in this component, we've got our wings, we've got essentially the outside of this body of the plane, and everything else is pieced together. But notice that on this side, we do in fact have engine flow through tagged. So if I click on the engine component, let's switch that to a wire view. And I'm going to essentially show only. We're going to look at just the engine part. It's a little hard to see with this wireframe that color. I think I might go to like a gray. That might be a little easier for everybody here. So if I zoom in, you'll note that this is a reflected copy. So the right side of the engine is the only part that's actually designed. Everything else on the other side is XZ symmetry. So here we've got the inlet. I've defined under the design tab, the inlet lip is here. The face is way back here, where I would assume that the engine begins. And then all the way back here, our outlet face is just at the beginning where the nozzle is. If I zoom in, those of you online can probably see it a little bit better. And then here at the back, we've got the closeout of the nozzle, and that's the outlet lip. So what I've got it set up as, I want the flow through in here. So I've got the outside of the engine, and then my interior flow path is all modeled as cross sections that pass through the inside of this airplane. I've got the flow through negative set, so now it's treating the entire inside of this geometry as a negative volume. That means that it's going to cut things away. Now, if you try and do this, I need you to be aware that sometimes, remember we talked about coincident surfaces, if you try and run CompGeom or CFD mesh or something without a tiny, and I mean tiny, little piece of, say, Y offset, it might crash because you've got a reflected component on the other side and both of those are negative volumes. It's going to try and self-intersect itself before it intersects the other thing, and it just gets messy. So if you want to do something like this, you can put like 1 × 10⁻⁵ or -6, something really small in, say, a Y offset, enough to make it not numerically exact, but enough to offset it. That should fix it. So what we're going to do now is I'm going to close this. I'm going to show the entire model. Here we go. And so now I'm going to run CompGeom just to do a simple intersection. We're going to ignore all the subsurfaces because we don't really need them for this. And hopefully this will work. It worked earlier when I tried it. I say that, and of course it's going to crash. Watch. Oh, it worked. Great. So this is our intersected mesh. And if we go to a hidden view, everything is tight. It is solid. But here's what's really cool. Let me fit this on the screen, hide CompGeom here, and go and shade this. If we zoom in and look, the inside and the flow path of those engines goes inside the jet, straight back to the inlet face, and it passes through all the way the body and comes out at the exit.
You might do a
So
clipped view to show it.
yeah, that's what I was about to do. So I'm going to come in here and use clipping, and we're going to trim everything with Z greater than a certain value. And I'm going to dial that down just a little bit. So right there, and if I jump to a top view, so inside this aircraft, when everything was intersected, the flow path of this engine was treated as a negative. So all of these triangles and meshes that you can see inside this body, the reason they're shaded brighter is because that's a positive surface. That's pointing essentially out of the volume that is contained inside this geometry. So you can set this thing up, send it to a CFD solver, define your boundary conditions, do whatever you want, and it will flow straight through this airplane. You could, although I really don't recommend it, try and run this through panel mode in VSP Aero, and it's a solid surface, so it should pass everything through, but maybe don't do that. It may work, but you're probably going to get something that doesn't make a lot of sense. But I really like this airplane. I like this demo because it shows that you can, in fact, run a flow path straight through something like a fighter, and you know, it does what you expect it to do. It's really, really cool. So let's see what time. We've got about 4 more minutes, I think, here before our next presentation, Rob.
Hey, Brandon, would you just repeat that comp geom, but with the representation, say, set to front face and aft face, or
Oh yeah,
or
sure.
negative
Yeah,
to front face and negative to aft face?
yeah. Let's do that as a quick demo. So we'll show that, and I need to turn off my clipping so I can. Well, maybe not. Yeah, it's going to bother me. I'm going to turn clipping off so I can see what I'm doing. All right, let's set that to a wire view. Go to top. Okay, so let's go to our engine, and we're going to change. So instead of flow through negative, we're going to go to face negative. Okay, again, the inside of this engine trimmed out. Outlet mode, again, let's do two face negative. So here, that's trimmed out, and this is all trimmed out to the face. So we're going to repeat the process that we just did by request and execute. Okay, so that seemed to work fine. Again, we'll go and shade this. So if we look, I should jump to a rear view of the airplane and do a fit. So if we're looking in here, again, this is kind of where that problem is. So we mentioned coincident faces. These two symmetric copies, the left and the right, are far enough apart that it understands these two are two different things. I know how to intersect these. The face is coincident. And so this is what it looks like when you have two right on top of each other. And so it breaks, but you notice that it kind of breaks symmetrically. So it's trying its best, but in order to make this really work, you'd have to either go in and close it off or trim everything up. But, you know, it would be nice if we could figure out like exactly what's causing that and choose it to just, you know, pick one. But it's not something that's necessarily been required up to this point. But again, here on the inside, you can see down inside the inlet of this engine, and it goes back and it stops here at the face. So
show the clipped view again.
Yeah, I'm going to go and turn clipping back on, so this C greater than. And so yeah, looking down on the inside, jump to a top view again. So we've got our flow path all the way up to the inlet face, and the outlet face is here and out. So if you have this, say, pulled into your meshing engine or your geometry setup for CFD, all you really have to do is tag that face, set your boundary condition as, you know, mass flow or whatever you want it to be. Same thing on the exit, and off you go. So really cool stuff.
Thanks, Brandon.
Absolutely. So I'm going to go ahead and close VSP here, and we'll get you queued back up for your community talk, Rob.
Great.
Let me stop sharing mine, at least as far as the Teams goes. There we go. All right. So, Rob, it's all yours.
Thanks, Brandon. I appreciate you going through the flow path conversation and demo. It's a relatively new feature. It has a lot of moving parts. It's not trivial to understand. Hopefully that helped people get it. And if they need the use case of, representing an engine in their model and, with different analysis tools, whether that's wave drag or CFD or whatever, that gives them the flexibility to build a model that will meet their needs. So that's certainly the hope. Changing gears a little bit, I wanted to talk a little bit about the OpenVSP community. This is not, just a little preface, this is not a complaint or a gripe. There's just some facts in here that may surprise people or may not. But we'll go through some of this, and I'd just like to point out an opportunity for everyone to help and make things better. So I'll just dive in. So VSP's history goes back to the early 1990s, developed at Ames. It was released as open source in 2012 as OpenVSP. And that's really when I forked it from sort of direct NASA control being developed in-house at NASA to being something developed out in the open. And when it was open sourced, some people asked me, Rob, how do you deal with all the flood of contributions and bug fixes and features coming in from all the community, right? Because that's how people think open source works. And again, not a complaint. I love my users, but that's not the way it works for OpenVSP. In some cases, you could imagine if you were writing a C compiler in the C language, then the Venn diagram of your potential users and your potential developers has lots of overlap. Someone who is a C programmer who uses a C compiler could potentially be able to contribute to and willing and interested in contributing to a C compiler written in C. But when we're talking about a tool for doing aircraft conceptual design, that's my set of users, people who do aircraft design, which is amazing. But then the skills needed to develop it are, really hairy 3D numerical algorithms and geometry algorithms in C++. And so, the Venn diagram of OpenVSP users and OpenVSP developers has very little overlap. And again, this is not a complaint. This is just an observation. And so, we don't get a lot of open source contributions, and that's okay. Again, we have users that are users. And development is also not free. People think that it's all a big volunteer effort in open source land, and that's really not true either. The people who develop it on OpenVSP, almost without exception, have always been paid to do so. And whether that was, me now as a consultant or when I was a professor, and I would then pay graduate students to work on it, or other contracts with companies like M4, development has been paid, and all the developers are sort of one degree of freedom removed from Rob McDonald. I do donate my time for things like support on the Google group, and I donate the web hosting and the web registration, some small things like that. But the time that goes into VSP, right, and the predecessor when it was RAM and not OpenVSP, those were all paid contracts and supported development work. And of course that controls where the development effort goes, right? The person paying the bills is the one who gets to pick which feature gets implemented next. So there's a lot of perceived, and some of these are real, barriers to contributing to OpenVSP, right? It is a daunting source base. It's more than 300,000 lines of C++. There's extremely little documentation, or as I like to say, the code is the documentation. The build system is complicated. We've got many, many dependencies, and all those libraries have to be compiled and all have to work. And that's a very complex build system. The code itself, to make big contributions, it gets into some really hairy cutting edge geometry and numerical algorithms. And frankly, it's such a large code base that for a lot of people, even if they want to do something simple, they don't even know where to start. And so the first thing I'll say is if you want to do something to VSP, ask. In general, I find that I can tell someone where to start. Hey, oh, you want to do that? This is how I would go about it. And I would start in such and such files, and you're going to want to modify this class, and that's going to interact with this other class. So watch out for that. And I can give that kind of advice. And in my experience, that advice saves about 2 weeks on whatever job you're looking to do. So I can really accelerate getting people started on projects. And I know this is daunting and scary, but at the same time, it's really not as bad as it looks. There's a lot of grad students out there who I see develop incredibly elaborate scripts and Python scripts and other tools to work around a feature that does not exist in OpenVSP when they could have fixed it in like 5 lines of code. So oftentimes the easiest way to fix something or the easiest way to do something is just to do it in OpenVSP. And there's all these barriers to doing that, but I promise it's really not that bad. And I can try and help. Speaking of help, documentation is something where OpenVSP it has very little. I try to make the user interfaces very intuitive so that a process of exploration and trial and error is going to be the best way to learn things. Brandon has made amazing contributions to create the VSP Ground School, that set of videos that walk through everything in small bites at lots of different levels of users from beginner to expert. But there's not a lot of traditional documentation, and I struggle with it. I struggle in part because, of course, I'm not exactly sure what documentation would be most useful. For example, I don't think it's useful to document what every single parameter does on every single component. The wing sweep parameter adjusts the wing sweep, and I don't really think that a paragraph telling you that wing sweep adjusts wing sweep is going to be beneficial. So that's one problem that I struggle with, is knowing what to document and at what level of detail. I also struggle with the question of, if everything were documented, would anybody be able to find it? If documenting VSP completely created a 400-page PDF document, would anybody ever be able to find what they're looking for? What are the keywords? Is it searchable? Is it intuitive? Searching doesn't matter if you don't know what the keyword to search for is. So there's a lot of struggles around making good documentation, but there's also opportunity to help. So about 2 years ago, I added the ability to have online help in OpenVSP, and most people probably haven't even noticed it because very few things have been populated with this kind of documentation. But the first thing that got it was the advanced linking capability. I wrote a document, sort of a programming guide for advanced linking. But I didn't just write that documentation. I wrote an entire ability so that people can easily add documentation to VSP. So in this case, if you look in the VSP source tree, in the source directory, there's now the help directory, and there's a file in there called advancedlink.markdown. MD is a kind of online file that has some very easy to use formatting built in. And the contents of that markdown file is this black screen over on the right, opened in a text editor. And so you can see the markdown is things like these 3 dashed lines and the word title to identify that as a title. Here's a link to a file to include an image. Down here we have a heading with 2 hashtags. And then we have a table with some vertical bars and colons in order to format that table. So this is what markdown looks like. We can even include something that will be formatted to look like it's C++. Oops. We can also format things to look like math. So we can include equations in here. So we can write this markdown file. And then what I've done is, if you then want to tell the advanced links to then show that markdown file in the constructor of the advanced link screen, all constructors for screens in VSP now have this. All you have to do now is tell it what's the file name for the help file. And we wrote it in Markdown but notice here it shows up in HTML, and that's because we're going to convert it from Markdown to HTML. So all you have to do to add help to OpenVSP is write a Markdown file and then put the name of that file on the constructor of the screen you want it to appear with. And you'll notice that then when we run that screen, when it's compiled, that screen will get a little question mark up in the upper right-hand corner. And that question mark will open up a browser and will show you that online help. And so that's all it takes to add help to any screen that you might want to. So behind the scenes, what happens here is if you have Pandoc, which is a utility that converts from one document format to another, it's sort of a Rosetta Stone of Markdown files. And so we use it to convert that Markdown file to HTML. So if Pandoc is found, what we're going to do is all the Markdown files are going to be copied from source help into build source help to the build directory. We're going to copy any resource files with them, so any image files that go with that. Pandoc is going to process the Markdown, creating the HTML, and then we're going to copy that HTML into the installation package, the zip file that you download from the website. We're also going to copy that HTML to source help HTML. So we're going to make an archived copy of that. So here's the source directory, the build directory, and this is a representation of the installation package over here on the right. So this is how the sausage is made, but this is how I copy things around. Now, if you're on a computer that does not have Pandoc, then what we're going to do is, since it can't convert directly from the Markdown, what it'll do is it'll copy whatever version of the HTML is in the source help directory. It'll copy that to the installation package. So what this means, let me back up, is if you have Pandoc, it'll work from that raw Markdown file, and it'll copy it then into the source and make that archived copy. And then that archive copy will be used for anybody who doesn't have Pandoc. So again, most people, this won't matter because the distribution binaries are built by me through a GitHub process that has Pandoc. And of course, on my machine, I have Pandoc. So you don't have to worry about all this for the most part. Now, you can actually, GitHub will render Markdown files and make them look pretty. And so you can actually browse on GitHub and go into the source help directory, and you can look at all the different help files that exist. And when you click on them, it's going to show you them with the graphics and with some formatting. And that's great. You can go and you can browse the help without any sort of additional, infrastructure. But you can even edit the files on GitHub. And so GitHub will allow you to edit and create files right there from the browser. And so if you wanted to change, if you find a typo in documentation and you want to make a change, you can just go to GitHub. You can go to that Markdown file. You can click the little pencil to edit it, and you can then edit that file online, make the changes to that file. And when you save it, it'll make a pull request and it'll send that to me to be included into VSP. And it's that easy to contribute to OpenVSP and to contribute to the documentation. And you can not only do that editing an existing file, but you can also do that to create a new file. So if you find that, hey, here's a GUI that I think could use some documentation. It confused me when I first used it, but I figured it out and I think I understand it, and my understanding would help other OpenVSP users. All you have to do is go to GitHub, go to the help directory, tell it to create a new file, create a new Markdown file, write your documentation, create a pull request, and you're off to the races. So I'll show some of this here in just a moment. And that's basically the gist of all this. And I'll do some demo just to show you guys what it actually looks like. First, I'll come to GitHub. So here is here's the GitHub page at the top for the OpenVSP project. And so to find the help, we come into the source directory. And we navigate from the source directory, we come into the help directory, and you can see here are the Markdown files that have been created. And if I click on one of them, like the advanced link, you'll see that it immediately renders that, and it shows it in a nice format. It formats the code, It formats, any equations, which I don't think this one has equations, but it formats everything just like it'll show up in the browser later on, and including links. So that's what it looks like here in GitHub. If we just do that, we can also come over here and we can edit the file. And to edit and do a pull request, you need a GitHub user account, and you need to be logged into that account. So you'll need to do that. But all you have to do is click edit, and here you are. You're in a text editor, and you can just come in and make whatever changes you need to do. You can preview what that's going to look like in Markdown, so that you can switch back and forth. And then you can come up here, and once you make some changes, you can commit those and create a pull request. If you want to put images in, then you need to upload those images to the images directory and just choose a file name that nobody else has used so that we don't have conflicts. Choose a unique file name, and you can upload. If we come here to the images directory, you should be able to add file, and through add file you can upload a file. So if you've taken a screenshot of OpenVSP and you use that to talk about it in your help document, you can upload that file here to the images directory, and then you can come here to the Markdown file that you're working on, and we'll just view it raw. And you can see here, this is what a link to an image looks like. And so you can format that as you want and create that file. Now, the other thing that you have to do in order to make this work, this is a little bit more in the weeds, but if you write documentation and you don't do this next step, don't worry about it. Just in the pull request, tell me that you didn't add the link to the screen constructor, and I can take care of that. But just to show you, if you want to do everything, you can just come in and, for example, that advanced link screen, here's that line of the constructor. It's right at the top of the file where that file name exists. And so all you have to do if you want to add that help file is just come in and find, which one of these screens it was for. The other one that we just saw was the set editor. So we'll come down here to the set editor screen. Let's see, set editor screen. And we'll see right here is the link to setedit.html. And so all you would have to do if you wanted to add one to something else, say you wanted to add something to the structure screen, you'll see it doesn't have a file name down here. It just has these empty quotes. So what you would do is you'd come in, you'd edit it, and then you'd come in and you'd say, this is going to be structures help.html, and then you would commit that change. So that's all it really takes to, and yes, I'm going to discard those changes from now. So that's all it takes. And of course, if you don't want to use the GitHub web interface, you can pull down a copy to your local machine. You can make these changes in your local text editor of whatever text editor you like, or your IDE, and then you can push them back up. But my goal here was to reduce the barrier as much as possible so that anybody could contribute this stuff. And I'll just go and run VSP. You'll see that in the distribution, this directory is just like you would download. There's nothing special here, but here's that help directory that includes all these files, including those images. So all that gets put, the infrastructure, the behind the scenes takes care of getting that all the right places. And if we run VSP and we come in and we come to the set editor, for example, you'll notice there's now a question mark up here. And when we click it, it loads a browser, and we can see that documentation that was contributed by Jason last year. Or we can come in here and we can go to the advanced link, and we can click there, and it pops up that advanced parameter linking documentation that we've been talking about. And so, this is a new capability for documentation. If if we end up with a lot of this, which is hopefully, I would like this to grow, and when we come here to this help directory, we're displaying it online. You have to click here on each one. But certainly there's also the possibility that we could have GitHub automatically process these Markdown pages and create then another documentation page, which would be a very friendly, way to come and browse these things. And certainly we have this index Markdown file where if we add these things to it, which is certainly something we can do. So we should come and we should add links to the set editor help and to the other help screens that we have, which I think is an attributes related, attribute explorer markdown. So we should add each of those to that index, and hopefully through that we can build up some documentation in another way. So with that, I can take any questions. This was a pretty short talk for this one.
Thanks a lot, Rob. We just had, excuse me, a couple of chats here on the side, but popped in. So one of them, I mean, get your input on it. There was a question about whether setting up the help makes more sense to kind of do it the old style on the wiki pages like we had done in years past, or if the kind of current and future push for any help is to set things up on the markdown pages. I was leaning towards the markdown and these help files. Would you agree?
Yeah, that would be my preference. You know, the wiki was good because it provided another way to make it easy so that anybody could contribute. All you had to do was ask me for a wiki username, and then you could have access and edit it. We used to have that open for everyone, but we got a lot of spam bot vandalism, and so I had to shut that down so that it's a request process. So if you want access to the wiki, just email me and I'll do it. The problem with the wiki, and not a lot of people did things, and of course it got out of date. This is always the problem with documentation. But the other problem with the wiki is we do have users who use VSP in an environment where they don't have an internet connection, whether they're on travel or whether they're on an air-gapped computer or whatever the other situation. And so the wiki wasn't always fully available to them. The nice thing about this system is that the help becomes, entirely integrated into VSP, and all of the files are copied along with the distribution. And while it does load in a browser, that browser, you'll notice here, is accessing a local file. It's not actually reaching out over the internet. So as long as there is a browser on the computer, it'll be able to render and show those files. So and then there's really nothing better than having that documentation, in the GUI so that you can click on that question mark and have it pop up. So that's why we kind of prefer the markdown files. The other, hypothetical advantage, if we had a lot of documentation, would be that the markdown files will always match the version of VSP that you're running. Whereas the wiki, there's only sort of one wiki for all users. So conceptually, if we had a lot of documentation and it was being kept up to date, and you wanted to go back and run an old version of VSP for some reason, then when you ran that old version of VSP, you'd get an old version of the documentation. And when you ran a new version, you'd get a new version. So having integrated into the same release process and the same version control has some nice advantages. But mostly, it's just about trying to lower the barriers so that people can contribute documentation. And what I would encourage, I've talked about my weaknesses of documentation, not knowing what needs to be documented and other things like that. Don't worry about, from your standpoint, if there's something that, you don't know the exact details, or you're worried if something's not correct, I'd say write something, put in a pull request. And I'm not just going to blindly put it up there. I'll go through and I'll edit it, and I'll make any clarifications, or I'll make any corrections if you get something a little bit wrong. But you starting that ball rolling and identifying this is something that needs to be documented, and this is what would help me. This is what would have helped me understand what's going on here. That's a huge help. And then I can just go through, and I can nitpick it and make sure that it's technically correct, in case you're worried about, if your understanding is incomplete. So that's the hope here.
Yeah, thanks for the insight there. And as you were talking, I was just reminded that someone emailed me, oh gosh, it might have been weeks ago now, and pointed out that the ground school, everything in the OpenVSP GUI, all of the help, everything is in essentially American English, and we have a lot of international users where, some of this stuff, the language barrier is a very real thing. And while that's not something that, you or I can tackle, I think with, some of the advent of things like, I don't know, a language model that happens to be particularly big, one could go through and maybe adjust some of these things to a translated version that was more accessible to our folks around the world that, maybe English isn't a first language. But since we were on the subject of the help, I thought that that would be kind of an interesting thing to bring up while we were recorded here, because I had almost forgotten.
Yeah, no, that's very true. I mean, so there are technologies that exist to make internationalization of software easier on developers. And so, for example, there are programs that you can manipulate a source code base with that'll go through and identify all the strings that are in a program. And then it'll dump those out to a text file. And then you can go through and come up with translations so that you can take that file and you can translate all of those strings, to French, to German, to Chinese, to Russian, to whatever you want, and you can create all these different things. And then when you compile it, it will then substitute. It'll go find where's that French string and it will substitute it in. So that is there are tools to help with that. Um, it would be a lot of work, and I don't anticipate that any of my past sponsors would pay me to do that. But certainly, if someone in the open source community, who had the skills in C++ to go through and build up that infrastructure to support translations, I would accept those changes. And then that would give the opportunity for then people of all the different languages that wanted to then just go create the translation. So the infrastructure first, the translations later, would be another great way for the community to contribute. I will give one warning. Um, we have had problems in the past where people are using a non-default locale on their computer. And so you can change your computer's locale, and that's a C term, a C programming language term, so that your locale will change some of the things. And so it's not just translation, but for example, it'll change the decimal point separator from a period to a comma in certain cases, and it will change things like how dates and times are displayed. Americans use a very strange month, day, year date format that the rest of the world doesn't like. And so I mention this because there have been some bugs in the past where people who've changed their locale to using a comma separator instead of a decimal, instead of a period for decimals for fraction separation, have then written out files that were incompatible. For example, I think like the step files and some of the other file formats. So I will say that if we go down this kind of internationalization path, there are some really strange and frustrating bugs that can come up because why does the file not work? And it turns out it's because the decimal points are now all commas. Um, but yeah, I think that would be a path that we could certainly head down. And I think in parallel to that, frankly, the markdown files might be a lower hanging fruit. There might be an easier way with less infrastructure to convert the markdown files than the all the strings in OpenVSP. But I think both are options. I will say that another place where users could contribute is simply the Wikipedia entry for OpenVSP. The Wikipedia entry is typically pretty plain and somewhat out of date. And I only mention it because if I remember right, there was a French Wikipedia entry for OpenVSP about 3 years before there was an English one. So maybe that's another data point. So it's a great question. I'm out of time here, so we're scheduled for our break. That means I need to go grab some lunch, and we'll be back in half an hour. And Tim will show us some of the other neat things that he's been developing.
All right. Thanks a lot. Good talk, and we'll see everyone here in 30 minutes. We'll be back at 3:30 Eastern, 12:30 Pacific.
We're good to go. Thank you. Just tell me when to start talking.
All right. So for everybody online, welcome back. It's 3:30. We're going to go ahead and hand things off to Tim Coot from M4 Engineering, where he's going to be talking about some of the feature developments and things that have been going on here recently with OpenVSP. So as I kind of clean the screen up here, Tim, you are welcome to take it away, bud.
Wonderful. Thanks. Thank you, Brandon. Yeah, so appreciate everyone who can make it out to watch this stream today. Always nice to be interacting with the VSP community. Anyways, yeah, my name's Timothy Kiewit. I work at M4 Engineering out in Long Beach, California, and we've been contributing to OpenVSP the last year or two now with the Navy contract. So what this is quote unquote other stuff for additional feature development. There is a grab bag of additional features that were requested that didn't really fit in any other sort of presentation. And it also coincidentally were the things that I had worked on. So we put them together in this presentation. It'll be a series of four topics. Let's go and hop on in here. So we have a new Geom browser. You probably have seen this in Brandon's presentation, if not in your own OpenVSP. Hopefully it's been working well, and I don't think I've heard any personal complaints yet, so happy about that. We also have geometry reparenting. Again, something else Brandon did use in his presentations, and we'll go a little bit more in depth here. And then two other features are cross-section aliases, which is similar to, say, a name tag or just changing the name of them so you can more easily see what they are. And a small feature, a prop direction visualization improvement. So let's start with the Geom browser. What we have here on the right side is your old Geom browser from a version or two ago. You'll notice in the browser itself, laser pointer. Yeah, the browser that I'm referring to is the box here. It says vehicle, hinge geom, pod geom, etc. And you'll notice it is ASCII art. So we have right carets, dashes, up carets, and it's entirely text-based. What it has evolved into is this, in which we have what's known as an FLTK widget. So FLTK stands for Fast Light Toolkit. It's been developed over the years as a open source graphics and GUI toolkit for C++, among other things. And it is super light, super fast. In fact, all of the other things we're seeing here are already FLTK. So we're just leaning a bit more heavily into its existing widgets. This one is called a tree. So we rebuilt it with that to expand its capabilities to cover some of the things the Navy wanted. So what we have now are clickable SVG icons, SVG being a vector type of graphic. We have open and closable, collapsible icons on the left. And we have a improved symbology all around. So when you're trying to see if something is attached to its parent with comp or UW versus not attached, that is delineated by the line style. And if it's a hinge geom, it'll tell you also if its children are attached to a hinge, because you could have a very tall list of geoms coming off that hinge, and you might not see what parent you're looking at if you're scrolling through this geom browser. So here it is in a little bit more detail. We have double lines for the hinge and a thick line for anything that is a child of a parent and also attaches in either translation or rotation. And then on the right-hand side, we have icons. We have show and no show as the left one. And on the right, we have a series of icons for going through the surface state. And the last thing about those icons is we also have an indeterminate symbol in case we have any sort of mixed state. And that will come up for the vehicle itself, or if you have a collapsed geometry parent and it or any of its children don't all have the same answer. So this collapsed pod geom, we know it and all of its children are visible, but we don't know what all of it and its children are for surface state. Same thing with the vehicle. It indicates that we have mixed state in both show, no show, and in surface state. And the last thing that was added to this were these the new buttons for reparenting. So we're going to go on into reparenting now. So what we have here is the geometry window from a PodGeom, just for reference here, because when you are reparenting, I'm getting a little bit ahead of myself, but when you are reparenting, the order in which you change rel versus abs or attached to parent can change the behavior when you're swapping a child from one object to another, or even promoting it to being vehicle level. And this is very similar to what Brandon was showing earlier in the day, in which you would change from rel to abs and then turn on or off the attached to parent to change the relative positioning of an item. That can also be used when switching the lineage of an item between parents. So this all sounds fine and dandy. The most important thing here is that all of the links and params are preserved when you reparent an item. In the olden days, if you wanted to change whether a geom was a child of an object or not, you'd have to cut and paste. And doing that would destroy the original object. And if you'd done a lot of work in your advanced links or anything involving the params of that object, you would then have to go back and rebuild those, which obviously is not conducive to flexible model making. And this goes beyond not just user error, i.e., in my case, I'll just mash the add geom button without realizing I'd already selected a geom when I did not want that geom to be a child. It also covers just the simple fact that designs evolve, and not knowing ahead of time where and how you want the hierarchy of your model tree to look is reasonable. We don't want people to be locked in immediately. We don't want people to have to go back and scrape up a bunch of work and put it back together from wreckage. So this is just a major convenience feature, and it should be pretty powerful and pretty useful. The last little asterisk here is that right now a conformal geometry is not supported by this. Okay. Oh, and one other thing, of course, with any new features we're adding, they are supported both in GUI and API. Just want to make sure that's clear. And those API commands are all documented online. They're all easy to find, and they have documentation of example cases. Okay, I'm going to move on to cross-section aliasing. So aliases are name tags. Again, a common feature of the things I've been working on are ways to keep track of your model. So an alias is a name tag that you can put on a cross-section or a cross-section curve. And these are to keep track of your intent. So if you have a list of 100 or 10 or 5 different cross-sections in your stacked geom or fuselage geom, you can then denote, okay, this one is the seat back bulkhead. This one is the cabin. This one is cargo bay. And that is important when you get to advanced linking and you start grabbing params out of a param picker. So you can quickly sort through and see the relevant params attached to the relevant part of the geometry you're working with. So one thing to point out that is a little bit of finesse here is the concept of the underlying object architecture here is we have cross sections or XSECs and then XSEC curves. And the object of an XSEC in the underlying code contains one XSEC curve, where the XSEC itself is the fencing between the posts, and the XSEC curves are like the bulkheads. They are like the posts themselves in the fence. So just keep that in mind when we're going forward, because if I mention XSEC curve, it might sound like I'm talking about what we would describe as a cross section. So I just want to be clear on the terminology here. So this display alias doesn't change anything about where it lives in the code. It's just a little name tag added at the end to help you find it. And of course, as always, there's API commands for getting and setting these names. So let's look at this example here. We have this general aviation fuselage. And in this fuselage cross-section number 2, we've given it the section alias of cabin. And the section here is what's shown in this green box, meaning the lofted section between these two cross-section curves. And then under here, we have the cross-section curve controls where we have a general fuselage. And I've called this one with an alias of seat back bulkhead. Now, any cross-section type geometry has GUI added to the appropriate tabs in their windows. And as we'll see in the next slide, the advanced linking screen now includes this as an option for auto naming. So from that same cross section, we have cabin for the cross section and seat back bulkhead for the cross section curve. So in this advanced link, we have one we call test link. And you'll notice in the PARM group, because we were trying to get the height of the cross section, that comes from the group cross section curve 2, seat back bulkhead. And then as an additional convenience feature, another toggle button has been added to the automatic naming controls here when you're adding an advanced link PARM reference. So if you just drop this in here with only alias selected, it will append height to the end of seatback bulkhead. So when you're typing in your code here, it's already set up, easy to figure out where you're coming from. Okay, I'm gonna move on to the last new feature that has been implemented here, which is a context-sensitive prop direction visualizer. So the standard propeller starts at 30 units, and that's a little bit at mismatch with the standard marker size in OpenVSP, and that is okay, except sometimes you just want to see the propeller direction without zooming in super far. So what this adds is a Boolean parm to turn on and off a scale marker that scales to the fraction of the propeller size. Now, notably, the actual arrowhead still scales in the adjust axis marker size in the view window. So that's just make sure you don't have it mismatch again. But it's just a little thing, but it's there for people working with their eVTOLs or rotorcraft, knowing whether you're having advancing the blades on one side or retreating blades on that side, all that stuff. Okay, I think it's about time for a demo. So I'm gonna close it down and open up some VSP. All right, so let's open other miscellaneous features. And we're going to start with, pardon me for a second here. Okay, we're going to start here with the Geom browser. And you've seen this before, you've probably already used this. Not only can you select an arbitrary pod geom or arbitrary geom, you can quickly toggle that visible, invisible, change its surface state between the different allowable states. So here we have wireframe, hidden, shaded, textured, if we had a texture, and none type, which just shows the contour curves, if you have those curves showing. So the important thing here is a lot of work was put into making sure this is flexible. So it's not just one item selected. You can grab and select a bunch, turn those on and off the same way. Say you have some on and some off, whichever icon you click on will index all of them according to that icon's next state. So we have a mix between show and no show. If I click on the show, it will index all of them to the next one, and all of them will line up on no show. Meanwhile, if we then click on no show, the next one will be show. So that puts that to show. And the same principle applies for the surface states. So the next one after shade here will be texture. All of them go to texture. The other thing to note, as was being explained earlier, is the concept of an indeterminate state. So we have this pod geom with 2 kids. They're mostly coincident. I just added them all in the same XYZ location for expediency. So I'm going to make this one invisible. And then I'm going to collapse this parent. And you notice this parent's show no show has gone to indeterminate, meaning it can't say for certain when you're glancing at this thing that they're all the same. So if you're opening up a model from one of your coworkers or from the internet and you're finding out some question marks, it means it's not going to tell you the whole story without opening it. And that's just a really quick way to look at it. And then, of course, if you click these on a collapsed parent, it then aligns it and all of its kids, just like if you were selecting all of them. Now, if anyone's been really eagle-eyed here, you might notice something strange, which is if you have any number of selections, but not the vehicle selected, the vehicle shows the state of the whole vehicle's indeterminate qualifiers. Meaning, if there's anything in the vehicle that isn't agreeing, these will show question marks. If I make these all line up, that'll be visible, invisible, visible. And then there is one exception here, in which if you select any number of items and the vehicle icon, it will act as a global control just for that subset. So if I select these two and then vehicle, it's then checking if these two agree. And they do. So it goes to no show and hidden, or no show and wireframe. Then again, control just that subset. So there's a lot of finesse hiding in here that can be used to tell you a lot about a model very quickly without having to spend a lot of time combing through things. And that's the intent here. It's designed to make sure you don't have to sweat trying to understand what's happening when you get something given to you. Okay, so that is the Geom browser's icons. The second thing is this thick line here. It shows whether it's attached to a parent. That's attached, that's not attached. That's attached, and that's not attached. Simple as that. Meanwhile, Hinge Geom will always have that double line. So let's go ahead and talk a little bit more about reparenting. I'm going to make this one visible here. Let's say we add another pod here, and we didn't want to add it as a child of this pod. So I'm going to call this one pod Geom 2, just to keep track of it so we know where it's going. All you have to do is click left and right. So this will promote it up a level, down a level, down a level. And if you've never used the sidebar before, it's really helpful for getting your models managed here. This one will put it to the top of the current level, this one to the bottom, this puts it up and down. So for people who are finicky about your model's hierarchy and sorting, this is a great way to get your ducks in a row, so to say. The intention of the reparenting GUI is that it keeps the item as close to where it is as possible when you're promoting or demoting. So if it's at the bottom here, it's really easy because it just stays where it is. If it's up 1, then it goes to the bottom, and it will do its best, but it won't be perfect. Yeah, just like that. And then the real finesse here is if this thing is attached. So say we have it's attached on UW here in both rotation and translation. What we can do is say we want to attach it to this one instead. So I'm just going to promote it, or I'm going to demote it to child of this pod Geom. And if I leave this same attachment thing without changing anything, it will pop on over with the same relative attachment location. If, however, I had adjusted this thing carefully to a place I like in actual global space, and I don't want to mess that up, but I do want to change the hierarchy, as we saw earlier, we can change to abs, promote, go back to rel. And now we have the same UW location attachment point here with a whole new set of displacements. And you can change that in whatever order you want. So you can move your stuff around both hierarchically and geometrically with the promote and demote in your reparenting. Okay, I think I'm spending a lot of time here, so I'm going to move along to the next part. And I'm just going to hide that. Next thing to do is look at the cross-section aliasing. So we're going to go to, say, this one here. And we're going to call this green section green. Cabin, sure. Cabin, aft, bulkhead. Okay, And you notice in the attributes editor down here, it's also updating. So it's a good quick way to see that that's working. So we're going to go to advanced link, and we're going to create a dummy link. And what I want to do is make sure we have automatic names. And we drag in height, and there we go. We have cabin aft bulkhead, which is the alias, and then ellipse height is the parm name. That's reflected in your group list, just like so. Obviously, you will have the same sort of GUI whether you're in a stack or a fuse or a wing or a prop. And the last thing to show off is the propeller visualizer. So say we have this side-by-side propeller thing. It's kind of hard to tell from the top where they're spinning. So I'm going to turn this on. And first off, you can see the markers here. Secondly, you go to View, go to Adjust, and you adjust axis marker size in case you need to further tweak it independently of the radius. And if for whatever reason you maybe have a very small propeller and you want to make the visualization vector even bigger, you can change that off of 1. I think that's pretty much everything for the demonstration here. So I want to thank everyone for their time and for paying attention here. Thanks everyone for attending.
Yep. Thanks, Tim. Before we close out, I know you did the demo of the reparenting and showed some of the aliasing. I don't know that we have a recording yet of attributes, and I don't know how much you went into
attributes, that will be happening on tomorrow morning at 8 a.m.
That's right. That's a different section. Yeah. Okay.
No, I do not have
a little later in the day for me here. I was up kind of early. But all right, so we've got that covered. Excellent. Thanks.
Yeah,
thanks
I'm very excited to share about that too. Yeah.
So okay.
Obviously, happy to leave the floor open for any questions, or even if there's just a Q&A with general VSP, space for that, of course. Thanks everyone very much. One thing I want to make sure I acknowledge is thank you so much for the Navy of the U.S. Navy's Navier for this wonderful contract we've been able to work. We've had a ton of fun over here. I've had a ton of fun. This has been delightful to work on this. So I'm very, very thankful for the funding to have contributed to this. So if anyone from that department is watching, thanks very much. It's been a good time. So I make sure I get that acknowledgement.
Good call.
Yes.
So I haven't seen anything in the chat pop up, but it does take a few seconds. Hey, there's Andy.
Yeah.
Yeah, he said he appreciates the demo and that the functionality of all that wasn't always easily discoverable, but to see the demo, I think it makes it more straightforward. So I appreciate the demonstration and the talk.
Wonderful. You're very welcome. Thank you.
All right, so we've got about 7 minutes or so before Rob's next talk, where we get into curve and surface modeling and kind of the underlying purpose of geometry representation and how we go about that. So if there aren't any specific requests for Tim to show any more of his features, Rob, is there anything that popped up from discussions earlier that is worth a quick 5-minute tidbit, or do we just want to pause for a moment and then we'll pick back up at 1 your time, 4 my time?
I don't have anything queued up that I'm thinking we need to get back to, but we can certainly leave the table open. If anybody has any quick requests for the next few minutes, then I can try and respond to them as well.
All right, everyone. It's close to 4 Eastern here, 1 o'clock Pacific. We're going to go ahead and move on with Rob's next presentation covering geometry representation. Again, if you have any questions or suggestions for brief demos that we might be able to do in between presentations throughout the week, post them here in the chat, or you can even make requests in the OpenVSP Google group. The link for that is here in the chat as well. Without further ado, Rob, you're welcome to proceed.
Thanks a lot, Brandon. Much appreciated. This next talk doesn't have a demo and isn't really something that has, say, a particular feature in mind, but it's a bit of under the hood, how things work in OpenVSP and why, and what that does for us. And I think there's some, at least to me, some really interesting design decisions and some things. And so you'll just have to bear with me. I hope some of you will enjoy it. So there's a lot of different ways that computers represent geometry. And perhaps one of the most common is what I'll call the bag of triangles, BOT. And this is a discrete representation of geometry. Every triangle is flat and discrete in and of itself. And this is the most common way used in applications like computer graphics and animation and games, not necessarily the way that's most common in CAD and engineering. Your triangle file might have connectivity information so that one triangle knows how to connect to its nearest neighbor, but not always. They can often be just sort of a whole bunch of loose triangles flying in formation. Significantly, there's no information about where these triangles came from or how they were formed. They're just a bunch of triangles flying around. There's a technique called CSG, constructive solid geometry. And this term is a little bit vague because it can mean different things to different people. But basically what it means is we're going to build a shape by combining a bunch of primitive shapes, things like, spheres, cylinders, cubes, and we're going to combine them through Boolean operations, union, difference, and intersection. And we'll have a Boolean tree to combine these together. And usually CSG tools are implemented on a bag of triangles. So they'll take that cube, they'll represent it as a bunch of triangles, and then they'll perform a union of it with the other components. And it, takes the primitives, makes a bunch of triangle components, and then it takes the Boolean operations of those to create a bag of triangles output. Those input primitives, things like that cube and cone and sphere, those might be parametric in position, size, and rotation, but they might not. They might be just a bunch of discrete triangles coming in. Sometimes you can save the instructions that created a geometry, and you can change the parameters and play them back. Typically, in a CSG tool, you do not have the ability to do complicated things that blend between components. Things like chamfers and fillets are not really an option. Here, I've shown a VSP-based CSG operation where the sphere is a negative component and the cone and the cube are positive, and we can go through and we can calculate that difference. And, for fun, I also used VSP to take that Stanford bunny, which is a standard file from the computer graphics world, and perform then the union of that bunny with the triangle, sphere, and cone, with the sphere being negative. Okay, another completely different way of representing geometry with computers is what's called implicit modeling. And so to contrast that, we'll also talk about parametric surfaces. So a little bit of an aside. A parametric surface, you define the XYZ of a surface as a function of parametric coordinates, typically U and V. And it's easy to evaluate the surface. You just sweep values of U and V, and you can evaluate XYZ. However, with a parametric definition, the Boolean operations, CSG type operations, are hard. And likewise, fillets and chamfering are hard. And it's hard to either determine whether a random point in the middle of space, some given XYZ in space, is that inside or outside of a certain parametric surface. And likewise, if you want to project that point in space to the nearest point on the surface of a body, that's also tricky. That's not obvious. Implicit surfaces, typically implemented as a signed distance field, instead of XYZ as a function of U and V, we have some function of XYZ, and the surface is defined where that function is equal to 0. And we'll typically then have a positive value as the signed distance when you're outside of it, and a negative value when you're inside of it. So the trade-offs of using an implicit surface are it's harder to actually represent the surface itself. You have to do a more complicated algorithm to actually generate a mesh that you can visualize on the surface itself. So it's hard to evaluate, and you use an isosurface extraction routine to do that. But on the other hand, it's really easy to do Boolean operations, and typically pretty easy to do a CAD-style fillet or chamfer using an implicit surface. An aerospace-type wing body fillet, where you want a lot of control over a varying radius, and the radius varies around that fillet, that's still a bit more complex in implicit surfaces, but still easier than doing it with parametric surfaces. And then, since you have this signed distance function, it's really easy to determine whether you're inside or outside of a body, and point inversion is actually pretty easy. So these are just pros and cons of the math underneath the hood. So in CAD, the most common way of representing solids and surfaces is using what's called a BREP, a boundary representation. And again, the definition of this varies depending on who's saying it. Some people would argue that a bag of triangles is in fact a BREP. But that's not the way most CAD people use the term. Most CAD people use the term in what I'm going to describe here. So a BREP uses both geometric entities and topological entities to combine together to define a geometry. And so what I mean by this is the geometry are either points, curves, surfaces in space, or even curves on surfaces. And they're typically a parametric surface. So they're done with a NURBS most often. So this surface in space, like this red shiny rectangle with a grid on it over to the right, that's a 3D surface in UV space, where that grid represents the UV coordinates. And so we have that surface, that curved surface in space. And then on top of that, we apply a topology. And so topologies are connective information. They're relationships without actually any spatial geometric information. So if you look at this cone on the right, I've drawn the cone geometry in black. That's sort of the geometry of the cone. But then the blue lines represent edges, and where the red and the blue lines go together, they form an edge together, and that blue line loops around one face and the red lines loop around another face. And so the topological information is really about, okay, these three edges form a face, and this edge running down pairs with the other edge running up, and together those form a face, form an edge. And so that kind of topological organizational information is part of a BREP. Now, up on the right, you notice in this BREP, I've on this NURB surface, I've drawn in blue, I've drawn that square on it. And so that square, the blue, is a curve on the surface of that surface. And then what you'll do in a BREP is you'll use that curve and you'll trim that background surface. You'll trim that surface in order to create that square patch that's sort of hovering there up on the right. And so that square patch, you'll notice that the UV parameters underneath it, that grid, doesn't end at a nice straight line in UV. There's different UV values available because it's actually a trimmed surface, and that'll become important later. But this is how most CAD works, is they use a full BREP with a NURBS underneath for curves and surfaces within this topology information to build stuff up. So we use both the geometric and topological information, and typically the user's unaware of this, right? When you're a user and you're working in solid modeling, you're in SolidWorks or something like that, you're not really aware that there's a BREP under the hood. If your CAD program was set up so that you have an operations tree that is used to build this up, you can go back and you can save and replay and change things parameterized. By and large, and it'll go through and replay everything. It's pretty slow compared to VSP updates when it does that, but you can have a model that you can go back and change things. And a lot of these steps can be parameterized. Now, some things can't be, because what'll happen is and if you've used CAD, you know this, you can back up a few steps in your operation tree, and let's say you filleted an edge, but then you make a parametric change. You make a geometry bigger, and that edge no longer exists because that edge, got bumped. And then you go back to replay your tree. You're going to have an error in your operations tree because the topological information changed. And so some things can't be parameterized, but lots of things can be in modern parametric CAD. Things like fillets and chamfers can be implemented, but they're hard. Again, as a user, you don't usually interface with that being hard, except, sometimes you're messing around in Fusion and you find some geometry where the fillet just won't work and it won't solve. And that's because it's hard, and Fusion's not that great. So that can be implemented, but it's there. And then typically you'll output this as a variety of different interchange formats, whether that's IGESTEP, Parasolid, or ACIS. But all of those mostly use a BREP as the underlying representation. Now, when we do this, if we want to represent, say, a planar circle in a BREP, you're usually going to use a trimmed surface. And so what you'll do is you'll represent that plane as just a simple UV parametric plane. It's a square as that NURBS surface. And then you'll draw a circular curve on that surface and tell it that that is a trimming curve. And what this does is you'll notice that nice grid that we have underneath the trimmed surface label. There's no place where those lines collapse onto one another. There's no singularity in that surface. The surface is a very regular, easy to evaluate surface. And you have no singularities there. But what you do end up with is when you trim that circle, there is a lot of floating point math that goes on with that trim. And when you connect it, you can connect it logically, right? Your topological information may connect that circle to, say, a revolved surface to make the end of a cylinder. And so you'll have a watertight connection because the trimmed curve on the circle is connected to the end curve of that part of the cylinder. But numerically, when you go to evaluate those NURB surfaces underneath, because it's a trimmed surface, you will have non-watertight issues. And this is just fundamental to working with a BREP. You're going to have gaps. And if you've ever dealt with CFD meshing, where somebody sends you a random IGES file out of their CAD program, and you pull it into your CFD mesher, and you've got all these really annoying gaps all over the place, and you have to do a bunch of geometry reparations, this is what's going on, is the trimmed surface likely creates a numerical gap that didn't matter for one program, but then does for the other. There's other ways to do this, though. For example, instead of using a trimmed surface, I could represent that planar circular disk using the complete surface extents of a Bezier or a NURBS surface. And by doing that, I can make UV instead use one of these two different topologies, either sort of this radial topology or this other one. And I can make it so that the entirety of this surface definition is used. There's no trimming necessary. Now, the trade-off with this is that in order to do it, there have to be singularities. These points have to run together and collapse at the point or at the poles here. And those singularities can give problems for certain tools later on. But the advantage of this is that the boundary here is analytically known, and we don't have the same watertight problems that a BREP would have. Now, we've talked about Bezier surfaces before, and under the hood, OpenVSP can be viewed to be using something called Bezier solids. And these are, a much less used, somewhat unusual way of representing geometry in 3D modeling. And there was, back before everybody decided that NURBS and BREP was the one true way to do things, there was a lot more debate on this. So back in the mid-'80s, there were people who worked on different ways of doing Bezier solids, and they gave them different names like trivariate solids, or they called it a hyperpatch. But this is really what VSP is doing in a lot of ways. And I'll walk through that. So if we start with a Bezier curve, we can define XYZ, a 3D curve, is a function of U. And so U moves along that. And this is a cubic curve. So there's 4 control points. And these 4 control points define this curve. And so we can take that curve. And then if we want, we can just copy those points, translate them down. And by setting up this network, we can declare that the U direction is still along that curve and the V direction is across it. And what we've done is we now have a Bezier surface. And in this case, it's cubic in the U direction and linear in the V direction because we've just moved those points down. And so what we see is we can go from a Bezier curve to a Bezier surface by turning a vector of points into a matrix of points. And we can move that on out. Now, instead of making that linear in that direction, I instead could duplicate those points 4 times. And now I have it cubic in both directions, where on the left, that cubic curve just happens to be a straight line. But if I bring those points down, I can then have something that is bicubic in both directions, and you can see curved in both directions. And so on the right, we have a bicubic surface patch that is in UV coordinates. Now, just like we extended from a curve to a surface, we can also extend from a surface to a solid. So what I've done here is I've taken that bicubic patch that we just had, and I've duplicated it and flipped it over the other way. And in this case, I've just moved it down a little bit. And so just like I took that curve and I duplicated it and moved it in what became the V direction, I've taken the surface and I've moved it in what will become the T direction. So now I'm just going to call it RST as my 3 directions, parametric directions of a solid. And so here what I have is a solid that is cubic in R, cubic in S, and then linear in T. And on the left, I've drawn them separated apart, but on the right, I've collapsed them together so that it's all sealed around the edge. And so on the right, what I actually have is something that's equivalent to a Bezier solid. It is a watertight solid that encloses a volume, and we have RST parameters that can navigate around and through it. And VSP actually represents this as a surface because what we do is we split it and we unwrap it. So we actually unwrap it, and you can see we sort of chop it down the middle and we unfold this kind of like a Pac-Man, and we unfold that surface so that now V runs down one side and back to the other, and U runs the other way. But we can actually, you'll see that we can actually treat this as either kind of representation. The advantage here is that by using the full extents of a surface in UV and folding it up in this way, we're representing a solid without having to trim those curves. So we actually get a much more watertight geometry than other approaches. So let's talk a bit more now about what VSP does. Every individual object is modeled with a single, complete, untrimmed surface. So every component is individually watertight. There's some asterisks, some exceptions. We'll talk about those if you want. And every surface is analytical. They're not discrete, with some exceptions. The exceptions being things like mesh geoms and the human geom. But all the things that were the main things, like pod and wing and fuselage and stack, they're all analytical and they're all individually watertight unless you don't want it to be. And so we have this wrapped Bezier surface solid. It's entirely closed, and we have UV parameters that wrap around it. And then we assign we build complicated things like an airplane by basically doing CSG. We do those Boolean operations, typically just the union, but negative components are subtraction. And we represent things with a Boolean union. And one of the things that VSP does to make it really fast is we don't actually do the math of that Boolean union until you actually need it. Instead, we just let the graphics card trick you. So when you do a shaded view, it looks like we've done the Boolean union, but we haven't actually done it. And then we'll do that later on we only do it when you need it. So when you run CompGeom, when you run CFD Mesh, we'll do that Boolean union and then continue on with the analysis, but we defer that until it's needed because it's a lot faster that way. Now, just like before, that complete representation of that disk meant we had to have degeneracies. VSP has to have surface degeneracies in order to be able to use this approach to represent a volume. And so you can look at this ball on the right. We basically have to have some degeneracy here at the poles where we pull that together. And you can think about this like trying to wrap a gift with a piece of wrapping paper, where the wrapping paper can be stretched or shrunk, but it cannot be cut. We're taking an entire rectangle UV space of a surface and wrapping it to some surface. Now, sometimes we have hidden patches that you may or may not know, but they're always there. And a wing is a great example of this. If we start at just a very simple wing at the bottom here with a flat tip patch and a sharp trailing edge, and we thicken that trailing edge, you'll see that there's a new patch that appears. Well, in VSP, that patch is really always there. It's always there. It's just that when it's a sharp trailing edge, that patch is collapsed and is completely degenerate, and you don't know it's there. But topologically, it's there. And as soon as you thicken that trailing edge, it appears. And you can turn that flat end cap to a circle. But if you do both of these things, you make the end cap round and you bring up a trailing edge flat. Now there's this little tiny semicircle patch that has to appear. And that tiny semicircle patch, again, it's always there. It's just usually it's completely degenerated down and it's all degenerate at this point, but it can blow up. And if you then round the trailing edge and round the tip, that little patch actually becomes a little part of a dome, and everything is there for you. Now, under the hood, if we take a wing like this one, we have patches from root to tip. That's the U direction. And then we have patches that start at the trailing edge, wrap around on the bottom, wrap around the leading edge, and come back to the top. And if we flattened that piece of wrapping paper out, we'd get something here on the right where we start at U equals 0 at the root. We come up the root wing cap. We come across the inner surface, the outer surface, and then we go down the tip cap. So in the spanwise direction, we actually have these 4 patches. And then in the around the chordwise direction, we start at the trailing edge. We go down the flat trailing edge. We have the bottom surface of the wing. We actually have a leading edge bottom and top that are all degenerate in the leading edge typically. And then we have a top surface, and then finally the trailing edge top. So we actually have, 6 surfaces that typically, 6 patches that will wrap around a wing in order to do that. And again, that degenerate wingtip corner that I said is always there is usually this little square down here in the corner. It's usually all collapsed to the same point, but if you need it, it's there. Okay, so when we talk about this as a parametric solid, we can do what we were talking about before. We can extract, instead of just extracting the top and bottom surface, we could extract an intermediate surface like this median surface in either direction. And so we can actually extract these things using surface math. And here's how we convert that to RST. U is the same as R. We separate the V into V lower and V upper, which is S over 2 and 1 minus S over 2. So those are matching things. That gives us X lower and X upper, which we then just do a linear combination. So this is that linear direction in that Bezier volume. And so that gives us the X. And so U runs from 0 to 1, V runs 0 to 1, R and S and T also run 0 to 1. And that gives us a volumetric coordinate. Now, these coordinates may not have uniform speed, right? U and V may go fast in some places and slow in others. You can usually see this by the spacing of the wireframe shown in VSP. But we figured when we were doing things like attachment volumetrically, you might not want that non-uniform speed. So we introduced the LMN coordinates. So what's going on when we talk about RST versus LMN? Here's some U being non-uniform, right? U starts at 0 and goes to 1, but in something that has these 5 patches, it goes to 1/5, 2/5, 3/5, 4/5. And you'll notice that the X distance between these is not uniform. So you have a non-uniform speed here. But what we can do is then LMN makes that more uniform. Some places you see sort of a dimensional version of U. And so there it's going 0 to N. So this would be section 2, where it goes 0 to 5. Or in the non-dimensional, this would be section 0.4. This would be U equals 0.4 because it goes 0 to 1. Okay, I've got a little bit more of a rabbit hole. I know I'm going long on time, but I think this is interesting. At least I like to nerd out on it. So let's talk about Bezier versus NURBS. And so most CAD and most geometry things use full NURBS surfaces. And on the left is a fabulous book copyrighted back in 95 and 97. And this is sort of the NURBS Bible. And if you want to get into computational geometry, buy yourself a copy of this book. It's great. But it's by Les Pegel and Wayne Tiller. And this is, I mean, it's called the NURBS book, but it really is the NURBS book. But interestingly, on the right, Les Pegel and Wayne Tiller, they wrote a new paper, and it's time to drop the R from NURBS. And so what they're saying here, this is a non-uniform rational Bezier spline is what NURBS stands for. And so that R is the fact that these are rational curves and rational surfaces. So let's talk about that, because they argue that you should drop the R, and VSP drops the R. We do not use the R in NURBS. So parametric surfaces, if you read the NURBS book or any other book about parametric surfaces, they're going to start and say that Beziers and piecewise Beziers, they'll say they are a flexible, intuitive, efficient, accurate, stable, convex hull, variation diminishing, degree elevation splitting, invariant under affine transformations way to represent curves and surfaces, right? So this is a fire hose, but basically these are all the great things about using Beziers. This is all the math and great things you can do with that. They'll continue in the next paragraph or the next chapter, and they'll say NURBS does everything from the above. They'll say it gives you everything of Bezier's, but it can also represent conics exactly. And so that means you can represent circles without approximation. And then everybody says, because of this, we're just going to use NURBS, and they move on with their life. And that's the standard answer for CAD. That's what most CAD programs use. In reality, what they're leaving out is there's actually a bunch of stuff that Beziers can do that NURBS can't or can't do very well. So there's actually reasons not to go with this default answer. So as it turns out, again, I'm going to get into the math, and I'm going to run long. But a Bezier curve, a piecewise Bezier, is equivalent to a polynomial function, which is just to mean everybody knows what a polynomial is. A Bezier is a different way of expressing a polynomial, and you can always convert a polynomial into a Bezier and a Bezier into a polynomial. They're one-to-one the same. A NURBS is a rational function. That's what that R is, which means it's a ratio of, in this case, two polynomials. So a curve is just f of t, but a rational curve is a polynomial f of t divided by another polynomial g of t. And we typically in CAD will use a subset of this because and this G has a bunch of weights. It has these weight values that are applied, and the F has weights, and we restrict those weights. We typically restrict the sum of the weights to be equal to 1. And so that kind of changes the math a little bit, but not too bad. But the fundamental thing is we're going from something that's equivalent to polynomials to something that's equivalent to rationals. And by getting to rationals, we get the ability to represent conics exactly, circles, but we lose other things out. And so if you do any modern algebra, there's this term called where a field is closed under certain operations. And what that means is for a polynomial to be closed under addition, that means that if you take two polynomials and you add them together, you get a polynomial as the result. So when you perform the operation, the result of that operation is a member of the same field. And so as it turns out, polynomials are closed under addition, subtraction, scalar multiplication, multiplication along each other, composition, differentiation, and integration. So these are things you can do to a polynomial, and therefore you can also do it to a Bezier. Rational functions are closed under most of the same things. They also have the advantage that they're closed under division, which is great. That's attractive. But as it turns out, because of this, since Beziers are polynomials, all of these things are true. Beziers are closed under all those operations. And the nice thing is that the order of the curve doesn't explode terribly. So that if a curve is cubic and you take its derivative, you get another polynomial. So you take a cubic polynomial and you take its derivative, we all know you get a quadratic, right? And so the order in the case of differentiation actually goes down by 1. Other operations it'll increase, but it's usually not terrible. NURBS, rationals we said are closed into the same things. Once you put that restriction on weights, it makes it a little unclear. But even if it wasn't unclear exactly what they're closed under, these operations become impractical on NURBS because the explosion of their degree. For example, if you take a rational that's cubic and you take its derivative, that derivative becomes sixth order. And you don't usually just want to perform one operation through these things. You end up doing many operations. And when you chain these operations together, if you were to do it using NURBS, you're going to end up with ridiculously high order things that have lots and lots of problems. And it's not practical to implement these algorithms. However, if you just stick with Bézier's, as it turns out, you can do a lot of really clever things. So let me give an example. If we have two curves, A and B, which I've drawn up here, and they're both in this case cubic, I can subtract these two curves. And as it turns out, it's just as easy as subtracting the control points in order from one another. And what I end up with is I've actually then synthesized a curve that is the difference. If you're at t of 0.5 on curve A and t at 0.5 on curve B, this becomes the curve that is the difference in XYZ between those at t of 0.5. So we can actually subtract those two curves. We can even then multiply those two curves together. And so we can take that difference and we can multiply them together. And so now we can estimate the error between two curves. And that's a fabulous thing. And we can then take those components, the different components, the x, the y, and the z components of the error squared, and we can add it together to come up with a scalar measure of the r squared between those two, of the distance squared between those two curves. And so if we want to write something where we're approximating a curve, we can actually do all of this analytically just by operations on the control points without degree explosion. And this is huge for doing geometric algorithms. Degenerate geometry can be enabled by this. If we have a very simple airfoil here with this curve, we can split that curve at the leading edge. We can reverse the upper curve. We can add them together, and then we can divide it by 2. And by going through that, we can actually extract a camber line from these two surfaces. Completely analytically, we can extract an intermediate surface for a degenerate geometry. Another one that comes up a lot in CAD is what's called point projection. And I apologize for our next talk. I'm going to run just a little long. I'm very sorry. But point projection is where you want to take this point here and find where on this curve is the nearest point. This is done all the time in mesh generation and other algorithms. It needs to be fast. It needs to be accurate. It needs to be robust. And if you're doing NURBS and most other things, this is done through numerical optimization. And so what they'll do is they will query the surface. They'll query the surface coordinate and its derivative many times. And they'll run a numerical optimization to try and find where is that minima point. And just like any other optimization, you'll get stuck in local minima, you'll have robustness problems, and this is really challenging and expensive. However, there's ways you can do this with a Bézier. We can do what we talked about. We can subtract that curve from the target point, and that'll give us now a new curve that is the parametric curve of the difference between them. We can square that and sum the components just like we said, and we can come up with them with a delta squared between these. And then we can take the derivative of that curve. And that's what I've shown over here to the right. This is now the derivative of the curve of the distance squared between these. And of course, where the derivative changes sign is going to be where your maxima and your minima are. So we can look at this very quickly. And wherever this curve passes 0, there's 3 candidates that we then need to look at for where is our point projection. And we're not done there. Since we have this curve now, we can use something called the variation diminishing property of that curve. And that basically tells us that in part of a curve, however many times the control volume crosses the 0, that's how many times the curve is going to cross 0. And we can use the split ability of a curve. We can split it in half. Here we've split it into red and black. And we have the exact same curve, but we split it in half. And now we can look at those, and we can use variation diminishing, and we can split it again. So here, without having to query the surface at many points, just by operating on the control points, we can bisect down in order to find small, short sections of the curve that bound one of the potential roots, which is, of course, our nearest point. And this allows us to defer, and once we've bisected and we've isolated a root, then we can run Newton's method on it, which is a numerical algorithm. But this combination allows us to do a partially a purely geometric algorithm for point projection and partially a numerical algorithm. And this gets us much greater speed, robustness, and quality in things like point projection. Now, there's a ton of other algorithms that OpenVSP uses under the hood that use these tricks that are enabled by dropping the R. And so instead, I would go back to that statement and say that piecewise Béziers are all those things we said before, a flexible, intuitive, efficient way of representing surfaces, but that they're clothed with practical applications under addition, subtraction, multiplication, division, composition, differentiation, and integration that allow superior analytical, geometric, and semi-numerical algorithms. And you can always approximate a conic to any degree of accuracy that you want. We can write them out as inerbs if you want inerbs, and it's a great way to represent curves and surfaces. And so I'm going to take any questions in writing and quickly turn it over so that we can start the next talk. But thank you guys for letting me go on this particular tangent.
Thanks a lot, Rob. That one's always a really interesting talk. Ken has already joined us here on the Teams call. So Ken, if you want to go ahead and get things queued up. Looks like the stream is just catching up to our roughly 15-second delay that we have on the stream here. So if anyone has any questions on some of the curves and surfaces and the representation that we have here, you're welcome to post them here in the chat while we get set up for Ken's talk.
Awesome, thank you for that. Can you hear me okay, and are you seeing the right screen?
I am, and everything here looks pretty good. Just give me one moment. I'm just setting some flags and making sure that our recordings and everything are broken up appropriately, because otherwise we'd have a giant 6-hour video that I'd have to cut up later. It's a lot easier to do this on the fly. All right, so that is going, and it looks like we're getting caught up here online. All right, so the recording is healthy, stream's healthy, and everything looks good to go. Ken, so you are welcome to go ahead and proceed, sir.
Thank you so much. Yes, so my name is Ken Decker. I'm a senior aerodynamics engineer at SpaceWorks Enterprises, and I'm going to be going over how to run aerodynamic analysis with Cart3D Plus and OpenVSP. So for those of you who are unfamiliar with us, we're a company, a small business located in Atlanta, Georgia. We primarily work on engineering services and consulting for both government and private customers, as well as offer a number of commercial enterprise software platforms. Our kind of core competencies as a company are in launch vehicle and reentry system design, as well as high-speed aircraft analysis. And so kind of over the years, as we've done this type of engineering work, we've developed a number of commercial software products that have kind of filled a gap in our engineering work, and we now offer the products that you see on this slide commercially. Today, we're going to talk about Cart3D, which is our commercial offering for CFD as a kind of a repurposed and extended version of the Cart3D distribution that's provided by NASA. So that's what we're going to go over today. So for those of you who are unfamiliar with Cart3D, Cart3D is an envisaged CFD software suite that was originally developed by NASA. It uses a fully automated volume mesh generation for analysis without the need for the user to provide a volume grid, and it leverages a number of state-of-the-art features like adjoint-based mesh refinement, gradient-based design and optimization, 6DoF simulation, and so on. Cart3D has been around for over a decade now. It has a very large user base across the aerospace community in the United States. It's available from NASA for U.S. contractors for U.S. government work. Where we kind of enter into the picture as SpaceWorks is we have come to an agreement with NASA to kind of offer a commercial distribution of that software so that people can use it for commercial uses and internal research and development. And as part of that, we've added some extensions to Cart3D that are relevant for this type of analysis as well that we've developed. So Cart3D Plus is how we're kind of is our name for the commercial distribution that contains all of the same Cart3D functionality that's distributed by NASA, plus some add-ons that we've developed to extend the capability. So those add-ons include our Scorch module, which is an add-on that's used to apply viscous and aerothermal corrections to Cart3D solutions, as well as an improved batch processor for improved scalability across things like large design sweeps, generating aerodynamic databases, and managing runs on high-performance computing. SpaceWorks is currently the only offer of the commercial license, but most of the kind of integration with OpenVSP that I'm talking about will kind of double for both the SpaceWorks commercial version and the NASA version. So we're trying to maintain backwards compatibility there as much as we can. And OpenVSP, since Cart3D has been around for a while, it contains a number of interfaces that can help automate the setup of Cart3D problems from OpenVSP geometries. So that's primarily what we're going to be going over today. So in general, OpenVSP to Cart3D integration kind of follows roughly a 3-step process. So the first step would be setting up the OpenVSP model like you normally would. We've talked a lot today about kind of an overview of how you assemble geometries and define components, and then start doing some meshing as well. OpenVSP and Cart3D work really well together, particularly for conceptual and kind of preliminary level design. This is primarily due to the lower computational cost of the InVis and CFD solver versus some viscous solvers, and our kind of added on viscous corrections kind of maintains that low computational cost while building out the data set a bit. The requirement to run Cart3D is that you need a watertight triangular surface mesh of the vehicle outer mold line, or OML. And fortunately, OpenVSP natively supports the process of doing this triangulation and exporting a few different ways, so that we'll go over some of that later. And so once you have kind of the watertight surface mesh, then Cart3D kind of takes over and takes that surface mesh and generates a Cartesian volume grid about it, runs the InVis flow solver, and then typically we would run with adaptive mesh refinement, or AMR, to have the refinement of the mesh be driven by the flow features. So it kind of takes some of the burden off of the analyst to have to mesh the volume grid to get resolution and where you need it. We kind of let the flow solver tell us where it needs resolution, and that kind of speeds up some of the engineering time associated with these runs. So just going over some kind of system requirements that you need in order to run all these things. So obviously you need an OpenVSP and a Cart3D installation. Either the NASA version or our commercial version will do for the flow solver. If you're using our commercial product, you'll need a license from us as well. Cart3D requires a machine that has a Linux operating system, so you can either run it on a Linux machine directly, or if you're using Windows, for example, you could also run it on a virtual box that has a Linux operating system, or on Windows subsystem for Linux, which is a pretty common way that we see people running it. The compute platform must have sufficient number of cores and RAM to run the flow solver. There's no hard requirement on what you need. It's really going to be driven by the size of the mesh and the time that you have to run your simulations. So a general rule of thumb that we carry around is about 7 gigabytes of RAM per million cells. That'll kind of limit the maximum mesh that you can run on a given set of hardware. And then the time that it takes for the simulation to complete will be driven by how many cores you have, what your memory bandwidth is on your system, and things like that. So just kind of soft limits, just depending on your needs. If you're going to run our batch processor, you'll need a version of Python that's 3.8 or later. And then for full visualization capabilities, we would recommend using ParaView and TechPlot, or some other visualization software that can handle 3D visualization of meshes. We do have some limited visualization capability built in using some external libraries, but you kind of get the full feature if you use one of those commercial platforms, or ParaView for an open source option. So kind of getting into how do you do OpenVSP and Cart3D integration. So the first thing you do is you generate your vehicle OML like you normally would. The OML can be assembled from OpenVSP components, like we've kind of been discussing today. And each of these components might have some design parameters of interest. So to kind of get the full, I think, power of using OpenVSP and Cart3D, it's nice to kind of use this for design sweeps. So if you have variables that you want to trade, or if you have even like for a given design you wanted to look at different control surface deflections, for example, kind of setting up the model to be parametric allows you to kind of take advantage of some of those features. And we can even include fine geometric details such as small protuberances if those are relevant to your problem. Just keep in mind that the resolution of your volume grid will be driven by kind of the finest features that are going to be in your problem. So here I'm kind of showing some snapshots of the GUI that would go into a typical OpenVSP assembly. And the model I'm using here, I just downloaded from the OpenVSP Airshow site provided by Elias GH, and the link is down there if you wanted to download it yourself. And then there's also a wiki for some details of how to do the mesh generation. I'll kind of give the highlights here, but that's also a useful reference as well that I'll include it. So again, Cart3D Plus, it only requires the model of the wetted surfaces of the vehicle. So OpenVSP does have the ability to have internal geometries like structural layouts or fuel tanks or things like that. Those things can be omitted, or if they're included, you'll just have to make sure that your mesh doesn't contain any internal mesh elements. It's only going to be kind of a watertight enclosed mesh of the wetted surfaces. And then also a nice thing is that Cart3D also allows for breakouts of loads, both force moments and heating by component. So if you have particular regions of interest that you want to do isolated analyses on, if you assemble them in your OpenVSP model as isolated components, that component tagging will be preserved in Cart3D. So if you wanted to do, say, you wanted global forces and moments, but then you also wanted to do a targeted study on, say, control surface hinge moments to size an actuator or wing bending moments, you can extract those loads as well, as long as those things are defined as kind of their own components in your OpenVSP assembly. So next, once you have kind of an assembly that you're happy with and a set of design parameters that you want to analyze, you can adjust the wireframe to set the resolution. This can influence the surface mesh resolution depending on what approach you use to generate the mesh. Some use it directly, some don't. And it also can provide, better kind of CAD representation of regions, particularly with higher curvature. So just kind of keep in mind that Cartesian Euler CFD does not require the same surface mesh resolution as a body-fitted viscous CFD, so it doesn't need to be as kind of finely detailed as some higher fidelity aero analyses, but really just enough kind of mesh detail to resolve features on the body that are of interest, like regions of high curvature, or corners, or those types of things. So once you have kind of the resolution that you're happy with, the next step is to export the surface mesh as a Cart3D tri file. Like I said, these things are directly supported by OpenVSP already, so I'm kind of showing an example of the export toolbar on the right there. The preferred export option is to use the .tri file, since that's what Cart3D uses directly. You can also use an STL file. Cart3D does have some utilities to do conversions between STLs and tri files that just add another step to the process. And one extra advantage of using the tri file is that it will preserve that component tagging. So if you did want to do those kind of isolated analyses on particular regions of the vehicle, you'd want to break those out. And so when you export the mesh, OpenVSP will dump the Cart3D tri file that Cart3D needs to run, as well as a .key file that basically just contains a text file that maps the integer tags that are in your mesh to the names that were defined in your OpenVSP assembly. So these are kind of just there so that you can interpret the results in Cart3D, mapping the IDs to the actual names that you define in your assembly. There's kind of three approaches to meshing in OpenVSP for Cart3D. The first one would be to export an intersected isotropic mesh using OpenVSP's CFD mesh interfaces. This is nice because isotropic meshes are good quality. And just keep in mind that the CFD mesh, there's options to export the surface mesh and the volume mesh. For Cart3D, you only need the surface mesh, which is nice. And this utility also has some options for fine-tuning the mesh, so things like defining sources and growth rates and things like that. If you want some kind of finer control over your surface mesh, has a lot of functionality that you can take advantage of there. Another option would be to export individual component meshes that are not exported. You can do this. You just have to ultimately make sure that before you run Cart3D, you have to intersect those meshes. Cart3D does have utilities that if you have unintersected meshes, that you can intersect them prior to running the flow solver. Again, it adds another step, but there might be some advantages to doing that in some cases. And then finally, you can also intersect the vehicle mesh using OpenVSP's comp geom feature. That's the one that I tend to use the most. Just kind of, they find that to be kind of the most intuitive, but all three of these kind of have their own advantages and disadvantages depending on the nature of your problem. So once you get the surface mesh out, that is kind of the end of OpenVSP's job, and that's where we kind of pick up the integration with Cart3D. So we have to kind of configure our Cart3D input files to make sure that our inputs are consistent with what's going on in OpenVSP, and that primarily relates to the component tagging. So for those of you who are Cart3D users, you might know that there's several input files that Cart3D needs that concern setting up the flow solver, setting up the mesh, setting up the component tagging. For the legacy Cart3D, you can edit those XML files that match components and groups based on the tagging information that comes out of that OpenVSP export. We also have a kind of in our commercial distribution, an abstracted way of kind of combining those input files into a single YAML file and automating some of the generation of those large sets of input files. So that's another option to do it as well, basically using the YAML file to update with all of the component information and flight conditions and so on. And then for our commercial distribution, we also have a CSV file that we use to run large batches, potentially, of flight conditions. So it's basically just a table of mesh names, flight conditions, and if you have powered surfaces, you can even add propulsive boundary conditions as well. And so that kind of is there to make it easier to run kind of large sets of cases if you wanted to do design sweeps or error databases or things like that. So once you have your input files set up, next step is to run Cart3D. Again, our commercial distribution has a command line interface to kind of simplify some of the processes for executing and setting up the input files for each flight condition. Cart3D uses, or a common way of using it, I should say, is to run adaptive mesh refinement. So here's kind of an example of what that looks like. The flow solver begins by generating a bounding box around your geometry based on your settings, and then subdividing that bounding box in order to generate a coarse flow mesh. So on the left would be an example of a coarse initial mesh that has a very relatively small number of cells for a given flight condition. And the goal here is to basically run the flow solver on a coarse mesh, identify flow features of interest, and run an adjoint solver that then computes the sensitivity of a metric that you're interested in, like drag coefficient, for example, and identify regions of the flow domain that are contributing to sensitivity of that metric, and then provide resolution in those areas specifically. So in this case, we're running a Mach 3 example to illustrate the process. This is going to be heavily driven by the presence of shocks. So as the adaptive mesh refinement goes through, it's going to identify that the shocks are driving the metrics that we care about and provide resolution in that region. So the intermediate mesh, you can see we've increased the mesh from 43,000 to 278,000, starting to get some flow features coming into resolution here. And then by the end, for this case, I ran 6 cycles that ended up with a mesh of 6.4 million cells. And you can see we have really dense, resolution near the shock, and by this time we're starting to see forces and moments level off, and that's a kind of indicating that we've gotten probably about as good of a simulation as we're going to get for this case. And so this kind of takes the engineer out of the loop of meshing, and that combined with the low runtime of the Inviscid solver as compared to a viscous solver, kind of it makes this a very nice tool for kind of quick trades in the conceptual and preliminary phases at a kind of a manageable runtime. So once you get the flow solver, if you have our Scorch add-on, you can take the Cart3D solution and apply viscous corrections to it. Our Scorch module works by essentially taking the Inviscid solution that comes out of Cart3D, running a stream tracer to identify regions of interest like stagnation points and attachment lines, and then mapping out streamlines and identifying running lengths on each point of the body based on the stagnation point or attachment line that a given point on the body sort of originated from based on the streamline path. And once we have that information, we identify engineering correlations for each sort of region of the body that we can then use to apply those viscous corrections. So this is done using boundary layer similarity solutions, kind of assuming that the Cart3D solution is a reasonable approximation of boundary layer edge properties, and that the boundary layer is relatively thin, so that the original geometry is a reasonable representation of the boundary layer edge geometry. And then we can use that to get skin friction corrections and use Reynolds analogy to get heating corrections from that. And so here's kind of an example of a skin friction and an equilibrium wall temperature distribution that you would get at the end of this analysis. And the thermal solver supports both fixed wall temperature analysis and radiative equilibrium analysis for those preliminary level thermal trades. So for post-processing, our Cart3D Plus package has some automated post-processing that's useful for kind of aggregating these large batch runs. So the first thing that we do at the top level is for a given batch, we aggregate the force and moment and thermal responses for each component of the body and for the full body and consolidate them into CSVs. For forces and moments, we break those out into pressure, viscous, and total contributions. And then we also include a convergence manager that outputs solver statistics for each run as well. So these will include things like if the flow solver failed and what error messages came up when it failed. It'll output statistics like the final mesh size if you're doing adaptive mesh refinement, and also the degree to convergence of whatever metrics it is that you're tracking. So this can allow the user to quickly screen large batches of cases to see, did some fail or did some not converge all the way? Maybe they need a couple extra cycles of adaptive mesh refinement. So it kind of makes that sort of process of wrangling these large database cases or large design sweeps a little bit easier. And then in addition to kind of the aggregating all of the top level metrics, we preserve all of the individual case post-processing statistics as well. So for each case, we'll output distribution files that you can use to analyze both the volume grid and the surface distributions in TechPlotter pair view ideally. And then we also include run files that contain histories of things like flow residuals or forces and moments, and then solver logs as well, so you can track individual solver messages, warnings, or errors for any particular case. So if you kind of use that top level CSV to screen cases, you can then kind of probe each individual case to extract particular information or troubleshoot that way. We've done a number of validation exercises internally based on some of our internal programs and vehicles. Also at this last SciTech convention, we presented a paper where we benchmarked the numerical performance and accuracy of these solvers. So I'm including a reference to that if you guys are interested in checking it out. Here's kind of an example of a calibration of our, or sorry, of a validation of our heat flux versus a RAN simulation for a launch vehicle taken along a slice down the center line. And here we can see that we're getting pretty reasonable agreement between a RAN solution and an Euler's plus Scorch solution. So the blue dots are kind of the Cart3D plus solution, and the red are the RAN solution. And so this is going to be, close enough for a lot of conceptual and preliminary level exercises to kind of identify trends and support decision making. And again, we have more kind of benchmarking and accuracy reporting in the paper. And then kind of what you really get from a kind of a procedural perspective with this is really a significant speed up in the computational cost that you need in order to get that, kind of order of 10% accurate sort of solution as compared to a RAN solver. So we ran a cost benchmark compared to a viscous solver. In this case, we used Fun3D on a couple of simple benchmarks. And so we can see that the combination of the inviscid solver having fewer governing equations and a more efficient mesh storage algorithm leads to a kind of a lower computational cost per solver iteration. And then when you combine that with the fact that the inviscid CFD solver needs significantly fewer cells because it doesn't have to resolve viscous features like boundary layers, you end up getting, potentially a 5 to 10x speed up with individual solver iterations, and that can translate to a couple of orders of magnitude speed up when you talk about how much wall time it takes to run a case to convergence. So this is kind of why I think Cart3D plus OpenVSP makes it a really nice pairing for preliminary design, because you can kind of, especially with the viscous corrections, get the sort of same breadth of data that you would get from a RAN CFD, but at a fraction of the cost, and that enables significantly more design space exploration or sweeps that you can carry out. So just kind of some wrapping up remarks. At Spaceworks, we offer commercial license for the NASA-developed Cart3D software. The OpenVSP integration works for both. So if you're a NASA user, all of the kind of setup and handoff to OpenVSP is the same. We've extended the software suite into a package called Cart3D Plus that includes all of the existing NASA functionality, plus some improved capability for viscous and aerodynamic heating corrections and an automated batch processor. OpenVSP readily interfaces with Cart3D to allow for seamless transition to go from geometry to a fully featured aerodynamic and aerothermal analysis, and it offers an excellent cost balance between the low cost of Euler CFD, but the breadth of data that you would get from a RAN CFD, which makes it a very nice pairing for kind of preliminary and conceptual design activities. So if you guys are interested in hearing more information, feel free to reach out. But otherwise, I'm happy to take any questions if there are any in the chat.
Ken, thanks so much for giving us that overview. I'm sorry for shorting you on time up front. The YouTube stream is about 15 seconds behind, so we'll give them some time. If anybody has questions to open up in the chat, we'll get to those. I've been a huge fan of Cart3D for a very long time. We had we had tri-files in it before it was OpenVSP, so we've had tri-files pretty much all along as far as most people are concerned. And I actually think you're underselling the difference between Cart3D and, in that case, Fun3D, just because what you're not mentioning there is that every single one of those cases in Cart3D is getting rigorous mesh adaptation through the automatic mesh refinement. And so in a case where you've got, like we were showing, strong off-body bow shocks, at every angle of attack and every Mach number that you run that sweep at, you're going to resolve those and you're going to have a very efficient mesh for that case. Whereas to get the same thing without any sort of adaptation, which is what I think you're comparing to, out of a traditional solver, you would need an extremely fine mesh to capture every possible off-body bow shock location, and it's just not practical. So, in addition to getting really great efficiency, you also get a rigorous mesh adapted resolve solution every single time for every Mach and every alpha. So that's really it's really a killer tool.
Yep, couldn't agree more. Thank you for that.
Still waiting to see if anything pops up here in the chat, so folks are still coming up. Appreciate the comments there, Rob, and I completely agree. Even going back to your welcome presentation about the right tool for the right job to make the decision and move on, being able to use something like this to make quick decisions at a fidelity that makes sense for what it is you need to know about. Like, that is exactly the kind of stuff that we were talking about here. So really interesting stuff, and I'm excited to see OpenVSP and Cart3D still working so well together.
Yep, just a testament to that. I kind of have phases where I'm a regular OpenVSP user and phases where I kind of don't touch it for a while. And so in preparation from this, I kind of, this is my first time probably in a year or so working with OpenVSP, and everything pretty much worked right out of the box. So it didn't take me long at all to go from kind of that pre-made example from the air show to, getting Cart3D solutions for the presentation. So I think it's a really seamless integration that's pretty well maintained and very useful to kind of have in the toolkit for those types of analyses.
Well, Ken, I'm not seeing any questions online, so I think we'll go ahead and cut it off for the day. Thank you so much for closing us out. And thank you to everyone online for participating in the workshop today. I'll see you guys tomorrow morning.
Yep. We'll see everybody at the next go around. Thanks for tuning in, everyone. We'll see you tomorrow.